Okay, so welcome everybody to this session. So this is going to be a 3-hour session and 3 hours is not a proper time in which we can learn OpenFOAM. So in this session we are going to share with you all the resources, and we'll also demonstrate you the examples which you can use to learn OpenFOAM. So I am Payal Mukherjee here from IIT Bombay. I'm working as a senior project manager at FOSSEE IIT Bombay. And with me, I have my colleagues, Evan Fernandez, Paris, and Pranay today, who will be there throughout the workshop. Okay, so let me just move on to my next slide. I apologize, my system is a bit slow today. Please hold on. Okay. So this FOSSEE project, the full form of the FOSSEE project is free and open source software for education. So why this doubly? Because FOSSEE project was launched by the Ministry of Education. At that time, it was Ministry of MHR, Ministry of Human Resource Development, by Government of India. And then it was launched as free and open source software for engineering education. But gradually we have spread, and we have reached out to branches or streams of education which are non-engineering as well. Okay, so we have many projects many software that are taught under the umbrella of FOSSEE, which are not mainly for the engineering students. For example, we have GIS, we have animation, and many more things which are not applicable to the hardcore engineering students. So here goes FOSSEE project. It is being developed at IIT Bombay and is funded by the Ministry of Education, Government of India. And we are working for the National Mission on Education through ICT, which we call the NME ICT. Okay. And because it is developed at IIT Bombay, FOSSEE is not only restricted to the students and faculty members of IIT Bombay. It's an open project for all. And I think all the Indians should take this opportunity, should grab this opportunity to participate in FOSSEE and take the best out of it. So it's a free project. You need not pay anything for learning. The resources are free. Everything is free. Okay. And so we welcome all the students of India to just come, participate in this project and prosper. Okay, so that is the mission on NME ICT that we are working. We are trying to reach out to every nook and corner of the country, even to the remotest part where the university or the teaching facility is not as as good as the top cities. Okay, but FOSSEE is there, and that is the mission or the vision behind the project, and that is the government's vision to promote learning through the use of free and open source software. Okay, and why FOSSEE? Why FOSS? Why this free and open source software? Because the knowledge of commercial software or proprietary software is like a book which you can read only when you are inside the premises of your college campus. For example, there are many software which are made free to all the students of the colleges. But that is the university version, or the institute is getting it for free. They have some collaboration with the company, and the company is giving it for free. But whenever you are passing out of that college and you are planning to join a MSME, or you are planning to start your own company, at that stage you will feel the pressure, you will feel the challenge that you will have to buy the licenses for those commercial software with a very high fee. Okay, and that this knowledge of free and open source software, FOSS, will help you. It is going to be a friend of you throughout your life. Okay, so whether you need or you don't need, this knowledge is absolutely necessary for all of us, for all the students of India, even for all the faculty members of India, and also the corporate. We also work with the corporate. So if they want to save the money wherever possible, they should actually switch to free and open source software. Okay. So now the main thing that we do at FOSSEE is training, and the training is on the skill-based education. Okay, so we focus on the hands-on part of the training of a software, so that you can actually learn the software and apply it and produce an output in the form of a project. Okay, we have many projects. For example, for the OpenFOAM stream of FOSSEE, for the CFD thing, OpenFOAM, we have many projects like case study, research migration, lab migration. So all these are the projects which are applicable for OpenFOAM branch of FOSSEE. For eSIM, we have circuit simulation. For DWSIM, we have some other chemical process simulator, DWSIM. There you can you take up the flow sheeting project. So like this, there are many output projects which will actually test your knowledge on the practical aspect of your learning, and like how much you have learned the software. That is we call the skill-based education, and FOSSEE is for that. So these in this slide you can see many tiles. I was just talking about the engineering and non-engineering branches of software that FOSSEE offers for training. So Scilab, Python, I think Scilab you all have learned, you all know about MATLAB. So Scilab is a free and open source version or alternative for MATLAB. Python is widely used by everybody for all the streams of education. DWSIM, Open Modelica for chemical, OSDAC for steel industry, FLOSS Arduino, and OpenPLC for free and open source hardware. Okay, GIS for the mapping the mapping is widely used by all the industry now. R, I just mentioned for the statistical tool and data analysis. Okay, we also have, I don't know, this slide is not complete. Yeah, focal. Actually, I cannot view the focal, some black bar is there. So focal is a branch of FOSSEE that offers animation related software, 2D, 3D animation and graphic design. So this is the table that compares what all FOSSEE offers, like Scilab, R, eSIM, OpenFOAM, and it actually compares with the commercial alternatives of all the FOSS that is widely used and are in demand, and what all we are offering. If you're interested in details, I can you can email me in the same email ID that I have given. I can share you this list. So we don't have much time to discuss these in details. Better we cut down this and focus on this workshop and the learning that we are all here for today. Okay, so in this workshop today, we will focus on the installation part. We will have a demonstration session where you will get to know how to solve cases. Our team members will show you the examples, and they will actually tell you how to solve cases. So by cases, I mean small problems in CFD, which is a basic that everybody should learn. All the students who are learning the CFD should know how to solve a small case, a small problem in CFD using OpenFOAM. Okay. I'll also at the end of this, towards the end of this workshop, I'll walk you through our website, and there you can find many resources that you can refer to learn OpenFOAM. This workshop is basically to help you to crack the screening task for the autumn semester-long internship that FOSSEE is offering. And also I'll learn how you can contribute in all our case study project, research migration project. We are also actually throughout the year we offer semester-long internship that begins around January, February. Then we have this summer fellowship, and from this year, OpenFOAM team is also coming up with the autumn semester-long internship. Okay, so these are all the projects in which you can contribute after you learn OpenFOAM. Okay, so I just mentioned case study project. In case study projects, the students, or it is open for everybody, for faculty partner, any CFD enthusiast can participate in all these projects. This is not only for the students. Okay, we have contribution from many corporate people also. So case study project is a project which produces output based on a small case or small problem on CFD. Research migration project is for the people who are into who are research scholars, who are into PhD and teaching. So this research migration project, actually the learners, they refer to a research problem which has already been published in a renowned journal, and they actually solve the same problem using OpenFOAM. So they just replicate the research problem using OpenFOAM. For lab migration project and OpenFOAM GUI, I'll not talk in this session because it is not relevant today. So today we are here only to start off the learning of OpenFOAM. And yes, so once you contribute in this case study or research migration project, you will be awarded an honorarium, a certificate, and the best part that you will be receiving is recognition in our website. It is the most valuable thing that any institute can offer to a student. Okay, because this repository is going to be there forever. And whenever you are applying for higher studies, whenever you are applying for a job, you can just refer to that website where your work, your name, your institute, your solved case study or research migration will be uploaded forever. Okay, so that's the best thing that FOSSEE offers to all the learners, whom FOSSEE trains. So with this, I'll stop now. I'll just stop my screen sharing, and we will move on to the next phase of this workshop today, which is the demonstration part. Okay, so I would request my colleagues, Evan, Paris, and Pranay to take it forward. So Evan, over to you.
Thank you, ma'am. Yeah. Is my screen visible?
Not yet. Now it is visible. Yes.
Okay. So is it in full screen?
Yes.
Okay, thank you. So good afternoon, everyone. Again, welcome to this workshop. So I'm Evan Fernandez. I'm a research assistant with FOSSEE IIT Bombay. So in today's workshop, we will first just give you an overview of what exactly is OpenFOAM and CFD as a whole. Then we will go ahead with the installation session. How will you install WSL on your Windows system? And then we will go to how to install OpenFOAM 9 and OpenFOAM 2412. I'll show you how to make an alias also, so you can switch between both the versions. So you don't have to necessarily always open one of those versions. Once that is done, we will go ahead with the demonstration. In this demonstration, we set up 5 cases from each domain. So you'll have one from aerodynamics, one from heat transfer, one from multiphase, one from turbulence modeling, and the last one from dynamic meshing. So stay tuned. We'll go ahead slowly by in this whole workshop. So the very first thing in CFD. So what exactly is CFD? As you know that it stands for computational fluid dynamics. In this, we solve some numerical methods using a computer algorithm to analyze some flow in very simple terms. So our numerical methods are mostly the Navier-Stokes equation for your normal flow simulations. So in this, we solve those equations iteration by iteration to get a desired outcome. So that is the main idea of CFD. And most of you may know CFD, you have it in your course as well. So you are introduced to it. So I will not go too much into detail. So we also know some of the applications of CFD. You have it in basically you'll have it in aerospace engineering. You'll have it in a mechanical field that is in your heat transfer. You will also have it in the space sector that is for your re-entry vehicles and all of those things. So before you make any product, you want to basically visualize it. How will it behave in a controlled environment? So through CFD, you can mostly predict how it will be before the actual product is pushed into production. So moving on to the next thing, that is OpenFOAM. So what is OpenFOAM, you might ask? So OpenFOAM stands for Open Field Operation and Manipulation. That's the very basic full form of it. It was developed by Henry Weller in the 1980s, and it's still being developed. Previously, it was basically you'll have two versions of OpenFOAM now. You'll have a .org version, that is the foundation version, and then you'll have the ESI version. The ESI version is the more up-to-date one. You'll have every six months some updates coming out, and you'll have new features in that. That's why we are going ahead with OpenFOAM 9, that is the ORG version, and with 2412, that is the ESI version. So OpenFOAM is a free and open source software that you have. Unlike ANSYS, if you've used ANSYS for any of your simulation, I think during your coursework, you will have been introduced to ANSYS, because ANSYS is the more commercial variant of doing CFD. But again, once you graduate, you don't have those privileges. So you have to go ahead with something that you can use. So OpenFOAM is the very existence of that. So you have OpenFOAM to basically it's since it's free and open source, you can do most of your simulations and everything that you can do in ANSYS, but here it is free of cost. You have multiple options as well. Unlike ANSYS, you are restricted to a very select solvers. And if you have to modify something, you don't really know in the backend code. But in OpenFOAM, you do have that privilege. You can modify the solvers based on your application. So suppose I have a heat transfer case and I want to introduce, say, another factor into it. I can open the backend code, modify that, and create my own solver. So those privileges are there in OpenFOAM. And it also basically, if you're starting off with CFD and you want to learn the physics behind CFD, not just clicking buttons. So OpenFOAM is good that way because it helps you understand what boundary conditions you're putting. You're not just simply clicking a button and not knowing what it does. In OpenFOAM, the person who's using that software has to know inside out what exactly they're doing. Otherwise, you will end up with just as Professor Chandan would say, colorful fluid dynamics. Yeah. So the process of CFD. So this is a very basic flow of how you go ahead with a problem. So first you have your problem definition. Once you have defined your problem, what you want to simulate, you go on to the geometry and meshing. In this, you will create your domain and everything in it. Once you've done that, you will move on to the solver selection, what exactly you want to solve in that whole domain. So if you want for fluid, you will basically select a solver that is most relevant for it. If you want heat transfer, you will have some additional parameters. So you will always select a solver for that. Once you've done that, you will set up your boundary conditions, and then you will move on to the solution. You'll check whether your solution has converged. Once you are once you are happy with your solution, you can go ahead with the post processing. Now, these are some of the problems that you face. It's not always a straight line. Sometimes you will reach till the solution phase and then you'll realize that something is not correct. So there are multiple reasons for those. First can be either your geometry and mesh. So you have to go back to your geometry, tweak a bit, change some parameters, and then go ahead with the same process again. If still it is not up to the mark, then you will go back to the solver. You'll check whether that is set. You'll check your boundary conditions whether those are set properly. So it's a back and forth process. If nothing is that simple in CFD, so you have to keep that mindset and you have to be a little bit patient. So in OpenFOAM, this is a typical case structure that you will have. Okay, so the very first you will have is a zero folder. In that zero folder, you will have your initial boundary conditions. This is where you will set your velocity boundary conditions, pressure boundary conditions. If you have temperature, then you'll set your temperature boundary conditions, and so on and so forth. Then you will have your constant parameters. Now, in your constant folder, you'll have everything that remains constant throughout your simulation. So those can be the turbulence parameters that you have set, whether you're going to run a laminar or a turbulent case. Then you have your transport properties. Those can be the fluid properties that you have, since they will not be changing during your simulation. If you have some buoyancy effects, so you'll have this gravitational parameters as well. So those will also remain constant. So all those things you will set it in your constant folder. Then lastly, you have your system folder. This is where you will have all your simulation parameters along with your mesh. So the block mesh dict will create your mesh. You'll basically make your base mesh if you're using SnappyHex. So yeah, your meshing is done with block mesh itself. You'll have then your control dict. This is where you will set your start time, end time, your delta t that you want to set. And additionally, if you want to set any functions, say I want to calculate force coefficients or any force, you'll see that in the demonstration sessions once we'll show that. So any of those post-processing utilities that you want to introduce, you will set it up in your control dict. And then you have your FE schemes and FE solutions. These are where you will change your relaxation parameters. If you have to introduce any of the algorithms or you want to change any algorithm, if you want to implement your custom algorithms, you can always put those into these files. Okay. So this was just an overview of how your case structure should look. Now, since, okay, we finished up 5 minutes early, so we can start off with the installation session. So I hope all of you have registered. So I think, yeah, since you all are registered, you must have got an email as well. Yeah, yeah. So in that email, what we've sent you, we had sent 3 of the installation sheets. In that you had your WSL installation sheet, you had an installation sheet for OpenFOAM 9, and you have an installation sheet for OpenFOAM 2412. So I hope all of you have at least tried to install WSL. Now I have already WSL on my system because I've already installed it, because if I would have to show it during this session, I would basically log out multiple times. So before you go ahead with this sheet, you have to make sure that you have the Windows subsystem for Linux and virtualization enabled on your system. To do that, you can type in your Windows system, turn Windows features on and off, and it will send you to this window. You can scroll down to the very last, and you'll see that virtual machine platform is enabled, and you have to see that Windows subsystem for Linux is enabled. These two features are necessary for installing WSL and OpenFOAM. So once you click those, it will ask you to restart your system. So you can click on OK and you can restart it. I'm not going to do that now. I already have. So once you've done that, you can go ahead with everything that is specified in this document. So this installation session will be a follow along. So you can side by side open your laptops and move ahead with me. If you have any issues while following any of these, you can raise your hand or put it in the comment box. Our basically CFD team will help you over there. If it's too big of a problem, we will take it up in the Q&A session that we have at the very end. Okay. So the very first thing you will do in this document is open your Windows PowerShell. So I'll type over here Windows PowerShell and run it as an administrator. Okay. So click yes. So as an administrator, it will show you on top over here that it's running as an administrator. So make sure you're in the administration mode. Then once you scroll down, you'll notice in step 2, it is written here WSL. Basically, you have to run this command. So we'll copy this, copy, and paste it. Now, when you're pasting anything in the terminal, just make sure that the space and everything is proper and you don't select these double inverted commas, because most of the time people end up selecting this entire thing this way and it gives an error. So make sure you only select the code, the line of code that is over here. Okay. And see the space also. Now see, after WSL, there's a space, and after install, there's a space. So you have to change that over here after install and add install. So what this will do is, once you run this code, it will execute a set of commands and it will start to install Ubuntu 22.04. So once you do that, it'll ask you to restart your system once again. So you will have to restart it, and then it will automatically, once you've restarted your system, it will automatically open one window that is your Ubuntu environment. It should look something like this. So if I type Ubuntu 2204, so it will open a system like this, and it will ask you to make your user ID. Now mine is already created. So when you're creating your user ID, you will basically type in your name, and then it will ask you to set a password. So when you are setting up your password, make sure that it is something simple that you will remember and write it down if you forget it. So save it something simple like 123 or 1234, because no one else is going to access your system. And when you're typing in your password, it will not show it in the terminal. So if I would have to, I'll show that while when you're running your installation thing, that time it will ask you to give your, basically you have to type in your password. So when you're typing in that password, make sure that you are writing it properly and it will not show in your terminal. It will ask you to again reconfirm that password. So that's when you type in the proper password once again. Once you've done that, it will again, most of the time it will restart your system. It will ask you to restart, or you'll have to just close this window and open Ubuntu once again. So once you'll open Ubuntu, it will show you this way, whatever name you set, and it will create your user for Linux. Once you are done with this and you've successfully done it, then you can go ahead with the second sheet. So this was for WSL. Then you can go ahead with the OpenFOAM 9 installation. So again, In this, you follow the set of commands that are given over here. So the very first one is, I'll show you this completely. For OpenFOAM 9, you copy this and you open Ubuntu. Okay. So now over here, I'll paste it. But notice that this command, even though it is kept on two different lines in the PDF, it's a single command. So it is all together. Okay. Okay. And again, in this command as well, notice the spaces between the code, between the lines. Because if you don't type in the proper command, it will give you an error while installing. So see, over here, it will ask me to type in my password. So this is where I'm typing in my password, but it is not showing. So I've typed in my whole password, but it has not shown anything. So this is just a feature of Linux. So keep in mind. So once you click on enter, it will install some things. Basically, this command will just create a repository and all that. So these two commands are there to create a repository. The first one will just link those things. The second one will create your repository for OpenFOAM. Again, copy this one. Again, just confirm that the space between each of those commands is proper. Okay. It will ask me to press enter. So once you click on enter, it will take some time to just unload all those packages that it has. Okay. So once that is done, you can select the next command. This will just update your whole repository. Okay. Enter. If you've not done this yet, I'd suggest that you do it side by side, because if you have any errors, then at the end you can ask us that as well. Okay. Then we'll go to the next command. We failed to fetch some files. There's a space between Y. Okay. Since I had OpenFOAM 9 installed, so it will not give me any problem. But in case you have any of the errors over here at the end of the sheet, okay. Okay. So in case you have any errors while installing, I'll show you a way to go about it. So you can type OpenFOAM 9 download. Okay. So the very first option that is there, openfoam.org, you click on that, scroll down, you can open OpenFOAM 9 for Ubuntu. And over here, so over here, it's the very same set of commands that they've given. So you can go, scroll down and you can see they've given some fixes for any of the errors that they get. So you can go about that and you can see if it clears your doubt, then you can basically go ahead. If you still are struggling with the installation of OpenFOAM 9, you can always email us as well. And there are multiple videos on how to resolve all of those issues. So YouTube is your best part. If you have any errors, you can always go onto YouTube, type in the thing, and you'll get some solution out. Yeah. So this is one way. Then again, we'll go back to the sheet. Once, okay, so this one is for gedit. we'll copy this. We'll paste this. Okay. So once gedit is installed, you have to add a single line in your bash rc file. Now I'll show you the bash rc file. So you can type gedit, or you can copy that code as well. We'll copy the same thing. Okay. So once you open your bash rc file, you have to scroll down to the very end. Okay. So over here, you have to add, just ignore this line. In your file, you will only have it till basically this line, that is fi. That will be your last letters in your whole file. After that, you have to add this line that we've given here: source opt openfoam 9 etc bash rc. What this is going to do is it will source your openfoam 9 every time you open your terminal. So if I were to open my Ubuntu terminal, it would by default open openfoam 9 only. But since we're installing two versions, we don't want that to happen. That's why we have something known as an alias. So an alias, it is something that we are giving a keyword, say OF9, and within that we are telling it to source OpenFOAM 9. Now, what does this line mean? I'll show it to you as well. So once you've done your WSL and everything, on the left hand side, you will have a tab known as Linux, and then you'll have Ubuntu 22.04. So if you were to open this and go to OPT, then you go to OpenFOAM 9. So this is what it will source. This. Okay. So if you see the code, source opt openfoam 9 etc. So in openfoam 9, I have to open etc, and in this I have my bash rc. So it is basically sourcing this particular file to run openfoam 9. That is what we're typing in this line. So in our case, we will type alias of9, and you will have basically the source openfoam 9. So you can type this in the 2412. I have written the same line. So you can always refer to that if it is too confusing in this particular document. So this one was for OpenFOAM 9. So I'll show you. Hmm. So when you're installing OpenFOAM 12, I'll scroll down. Use, yeah. So over here, I've written the proper thing, how to basically add an alias for OpenFOAM 9. So you can refer to this as well. You can copy this line and paste it into your bash rc file. Okay. So once you're done with basically adding this line of OF9 in your bash rc file, you can close this, you can save it, and then you can close it. Once you've done that, you can type source, or you can copy this command over here. Okay, so you can paste this source. And once this is done, you can close your terminal and basically restart it, Ubuntu. Okay, so now every time I open my terminal, I would have to type OF9. So that will source OpenFOAM 9. Now after this, if I want to check whether my installation is done properly, I can type block mesh and then press enter. But then obviously you have to go into a run direct. So the very first thing you will do once your installation of OpenFOAM 9 is done, you will make a directory, basically a run directory. So you can do mkdir space p. Again, these commands are given in this installation sheet. So you have to make a directory. Everything is explained in this sheet as well. So you can do mkdir space dash p. So let's copy this and paste it. Okay. So again, see, make sure that the space is properly put. Otherwise, it will give you a command not found error. Okay. So what this has done is it will create now in 22.04, you go to home. In this, you'll have your own name and then you'll have OpenFOAM. So in OpenFOAM, it will create in your OpenFOAM 9. Now I have additional files. It will create a run directory basically. Why is this run directory needed? It is because when you're running any simulation, you OpenFOAM might not give all the permissions to the files because you can't modify each and every file. Otherwise, you will, if say suppose you modify some source code and then you can't revert it back, it will give you an error. So that is the reason why we create a run directory. So that run directory, it has all the permissions, you can say, to run a specific case. So in that you can modify all the cases, you can modify each and every file, and you can save those. So this run directory is made for that very reason. So to access that run directory, you just have to type. Once you've done mkdir and created your run directory, you just type run and you press enter. By default, it will, if you're in OpenFOAM 9, it will take you to OpenFOAM into your this, and it will take you into your run directory. Okay. Now in this run directory, again, there are a set of commands you can run. So in this command, you are basically copying a tutorial case into your run directory. So in this command, just when you're copying it, notice that there's a full stop at the end. So you copy that full stop as well. What that full stop is for, suppose I copy it and paste it. Okay. Again, just check the spacing. Hmm. So what this is doing is basically your cp-r is saying that copy -r, that is your entire directory or that entire file from, that is your foam tutorials, that is a tutorial file, into in that you have your incompressible file. Within that you have a simple foam file. Within that you have a pitch daily file. So what you're doing is copying this pitch daily file, and this full stop, it means that in whichever file you currently are, now we are in the run directory, it is copying this pitch daily into that run directory. So that's why there's a significance of that full stop. So kindly note that when you're copying anything and that full stop is there, copy the full stop as well. I'll show you where this whole directory is. So once you install OpenFOAM, so let's get home. Okay. So in OPT, OpenFOAM 9 will be there. In this, you have tutorials. So these are a set of basic tutorials that you have, because if you have to create any file, you will choose one of these tutorials. Now, say I was supposed to create a simple flow in a cylinder. So I know that my flow is of of low Reynolds number. So I will have an incompressible flow. So I will open incompressible. Over here, you can choose the different solvers that are available. So you have icofoam, you have pimple foam, you have piezofoam. Icofoam is your incompressible foam, but this is a transient solver. Okay. Piezofoam is your pressure solver. Same goes for pimple foam. And then you have simple foam. Simple foam is your laminar case solver. So we'll click on, say, suppose simple foam. In this, we have the pitch daily. So this is the same file that we are copying into our run directory. So you can manually copy it as well. Like say I was supposed to copy it, say Control C, Control V. I copy it from here and I paste it into my run directory. Okay. I can do it manually as well. Okay. So say I was supposed to paste it manually. I pasted it manually. But on Windows, when you copy paste manually, or you're basically copying it physically and going there and pasting it back again, you will have an additional file called this zone identifier. So you see, in all of these zone identifier files are there. These are not necessary. You can delete them. But then again, if you have a very large file, you will end up spending more time deleting these files than doing any actual practical work. That is why you have these commands. When you copy using these commands, it does not copy that zone identifier file over here. So you'll have a clean case and you don't spend time deleting unnecessary files. So yeah, this is one reason for going ahead with such commands. It's simple. In the beginning, you'll find it's a bit overwhelming, but as time passes, you will get used to this. So you will have, so okay. So once you've done this, since we've copied this, we don't really need this anymore. Okay. So I would do CD and then enter the pitch daily file. So your CD is to enter a file, whereas CD dot dot will be to exit a file. So these are some basic commands that you have for not for OpenFOAM, but for Linux as a whole. So you can always use these simple commands to go back and forth instead of opening multiple terminals. And you can always use your top arrow key or your down arrow key to basically view your previous commands that you ran in your terminal. So if I were to press my top arrow key, I know that I've pressed CD dot dot. If I again press top arrow, I know I've pressed CD pitch delete. Now these are all the things that you can do. But since we've just installed it and we want to just verify your download is done properly, you follow the sheet that is given over here. So we've done CD pitch daily, then we do block mesh, simple foam, and then we open parafoam. So we'll open this. So first we'll do block mesh. So we've created our mesh. Then we will run the solver name simple foam. This will basically solve the whole equations, everything, and it will give you an output. So the simple foam solver, as I said, it's a steady state solver. So after 287 iterations, the whole simulation has converged. If I were to solve it with icofoam, it would go all the way up to the end time. And then you use parafoam. So you can, yeah. So once you do parafoam, it will open parafoam. You click on the apply button on the left. It will generate your file. You have the 2D case. Then on top over here, you'll have VTK blocks. And in this, you can click on U. Okay. And then you can click the play button. So this will run your simulation. I hope you can see this because I can't really make the font size big on this tab because ParaView has its own set of settings. So yeah, these all are there just to check whether your installation is done properly. Because sometimes when you install OpenFOAM, if you're on Windows 10 or any older version, when you install it using these commands, sometimes it may give you an error, like your ParaView might not load, or say your OpenFOAM is not installing properly. So as I said, YouTube is your best place to search for a solution. Otherwise, there are OpenFOAM forums as well in which they try to resolve all of these doubts. And if you still are facing any issues, you can always email us. Yeah. So this was to install OpenFOAM 9. Okay. Uh, Now for OpenFOAM 2412, it is the same approach, but there are a different set of commands that you have. Since this is an ESI version, so the set of commands are a little bit different. So the very first thing is I've given you two commands. One is a curl command, other one is a wget command. So whichever one is working for you, you can go ahead with that. So in our case, I'll go with curl. So I'll copy this. So this, once your OpenFOAM 9 is done, you can close this terminal because then we know that it is running fine. So let's open Ubuntu again. This time we won't type OF9 or anything. We'll just directly paste this command. Again, check whether the spacing is proper. So after curl, there's a space S. We'll just verify this. Yeah, curl space S. Again, it will ask me for a password. Okay, so in this, my repository is set up. So now it is ready for installation of OpenFOAM 2412. So if your first command works, you don't have to do the second command. It's only an option. If the first one does not work or it gives you an error, then only go ahead with the second one. You don't have to run both. Okay, then we just update our repository. Copy. And then you paste it. This will update the repository that we've already set properly. Okay. So once that is done, you go on to the installation. Copy. A note in this command when you're installing OpenFOAM 2412. The ESI version allows you to download different versions of 2412 itself, depending on what you want to do with it. So if I were to type default at the end over here, as it is typed here, default, it will install OpenFOAM 2412 with the tutorials, with all the tutorials and everything that is there for OpenFOAM 12. But if I were to delete it, only OpenFOAM 2412, like how we did for OpenFOAM 9, this will only download your OpenFOAM skeleton. You can say like skeleton version of OpenFOAM 2412, because some people might not want the tutorials. They just want to develop something on their own. So for those people, you have different version. You also have a dev version, DEV, that is for developers. So again, you can always go on their official website. I'll show you that as well. So first we'll just do this. We'll type default and you press enter. It will again ask you whether you want to install or continue. You type Y, that is your yes, and then you press enter. So while this is being done, you can basically search for OpenFOAM 2412. So yeah, so this is under the openfoam.com version. Okay. So you can open ESI version of OpenFOAM 12. On top, you can go to download and you can see for, let's say, Linux. And for over here under Linux, you click on Debian or Ubuntu. So see, you can run these commands as well. It's the very same thing. So see over here, there's a OpenFOAM default because they want you to install the tutorials as well. So if you can scroll down, you can see that there are multiple versions at the end. Yeah. So see, the minimalist version is your OpenFOAM 2412, whereas the traditional version in which you'll have your tutorials and everything, basically traditional will be your developer version and everything will have basically everything, your default version that will have your tutorials. So these are the three versions in OpenFOAM 2412 itself. If you want to download, say, an older version, say 2112 or 2012, you can just, while installing over here, you can just type instead of 2412, you can type 2012. So that is the only difference that will be there. Okay. Yeah. So see, once it is done, you will basically get this message, triggers and everything. Again, if you've already installed gedit for OpenFOAM 9, you don't need to do this again. This is if you've not used gedit. And also if you want, optionally, you can install ParaView. Okay. I'll suggest that don't install ParaView yet. First check whether your OpenFOAM 2412 is installed properly. Only then go ahead with ParaView. So you do one thing at a time. Otherwise, you'll end up installing ParaView and it'll have a problem later. So again, you open gedit and you have to open your bash RC to basically add this alias. Now you have an alias for 2412. So let's do this one. I had already created an alias for 2412, but I'd never installed OpenFOAM 2412. So let's do that. So scroll down to the very end. You have an alias for OpenFOAM 2412. In this, it is sourcing USR lib OpenFOAM 2412 and the bash RC in that. Now, in OpenFOAM 9, you know that the file is in the OPT folder. OpenFOAM 9 is in your OPT. Okay, so if you were to find any tutorials, you'll go to your Ubuntu, you'll go to OPT, then you'll go to OpenFOAM 9, and then you'll go to tutorials. But for any of the ESI version or the .com version, if you have like 2412, 2312, or 2212, you will have it in a different folder. So if you scroll down, you will see there's a USR folder. In this, you have to go to lib. In lib, you scroll down, you will have one OpenFOAM folder. In this, you will have OpenFOAM and whichever version you have. So OpenFOAM 2412, and in this you have tutorials. Now, if you see, compared to your .org version or your OpenFOAM 9, you will have some additional basically additional tutorials. So if I were to show you in compressible, you will have, say, see this, in 2412, you have an acoustic foam that is to compute your sound waves in using OpenFOAM. Whereas if I were to show you in OpenFOAM 9, under tutorial, under compressible, there is no acoustic foam. So depending on your application, you can choose between both these versions. Now OpenFOAM 9 is still an older version, so you won't have all the features that you want. That's why we have told you to install both the versions. So if you were to do some advanced computational fluid dynamics that requires you to have some solvers that are capable of doing that, and you are trying to do such a thing, so it will be advisable that you go with 2412. Whereas if you want something that is really basic and traditional and you just want to learn OpenFOAM, OpenFOAM 9 will be great, because OpenFOAM 9 has most of the file structures and everything to the videos that are available online. So you won't have much of a mismatch. So if you're starting off with OpenFOAM, you can go ahead with OpenFOAM 9. And then once you are basically confident enough in OpenFOAM, you can go ahead with the 2412 version. Okay. Yeah. So once you are done with this alias, again, save, close, check the next command that you have. Again, then you source your bash RC. Your source is basically just updating that bash RC file. You can even close your terminal and do that. It automatically updates once you have opened your terminal fresh. So once you do source bash RC, you can again close your terminal, restart it. Now, if I type OpenFOAM 9 and I type run, okay. So now see, I am in my OpenFOAM 9 run directory. Now, if I were to type OpenFOAM 2412, okay. So let's say we do cd dollar home. Okay. Hmm. So then over here, I do OpenFOAM 2412. I still have to make my directory. So I'll again run this command mkdir space p. Basically the same thing that we did for OpenFOAM 9. And then you'll create foam run. Okay. Now if I were to type run, it would take me to my run directory in OpenFOAM 2412. So you see, if I type OpenFOAM, basically OF2412, and I type run, then I will enter the run directory of OpenFOAM 2412. If I were to type open OF9, then type run, I would end up in my OpenFOAM 9 run directory. So see, this way you can have multiple versions. I'm not saying that you can only have OpenFOAM 9 or 2412. You can have many versions. If you want OpenFOAM 12, you can install that as well. If you want OpenFOAM, say the new 2506 is a little bit different in the installation. So you can go ahead with 2312, 2212. The same steps are there. You just have to change one letter or one number that is over here. So instead of installing 2412, you can install 23, 22, 21, 12. So this is just an overview of how to install OpenFOAM. Now you can verify again. You can either manually copy the files from your tutorial for OpenFOAM 2412, or you can again run this command. So we'll do cp-r till the full stop. Okay. Copy, and then we'll paste it. Again, check the space, enter. So if I were to show you now, if I type ls, it will show me pitch daily. That means there is a file in my run directory. So I'll again type cd pitch daily. Now I'm into my pitch daily folder. So in this, if I can show you, there's again a zero constant system. I'll show you the file structure as well. Okay. So if I to type tree, it will show me which files are there within this zero constant system. So as I was saying, you have your zero. In this, you have your boundary conditions, basic boundary conditions, initial ones. So you'll have you basically a velocity. Uh, if there's any turbulence parameter, so you will have your epsilon, k, nu tilde, omega. Then you have pressure. Then again, in constant, you have transport properties, turbulence, all of those. So again, we'll verify whether the installation is done properly. So we'll do block mesh. Then you do simple foam. This will run again for some time. Okay, so 281 iterations, then it converged. Then you can open it in para view. Okay, click on apply. You can again see the same thing that was there in OpenFOAM 9. Okay. Now, in case when you type parafoam and it does not open paraview, or it gives you an error saying that it cannot find paraview or parafoam in the sheet itself over here, parafoam. In case you get an error, you can install paraview manually using this command. So install, you basically sudo apt-get install paraview. Same command is there on top as well. Sudo apt-get install paraview. So if you're facing any errors while loading paraview, you can install it manually. It will take some time because it has to unload many of those packages. Because paraview comes with multiple packages, so it will take some time. Okay. Yep. So these are the basic ways of installing OpenFOAM 9 and 2412. Okay. So again, if you want to install any of the later versions, so you can download, say, OpenFOAM version 13. Again, you scroll down, click on Ubuntu, and then you can follow this. Note one thing, that when you are installing any of the higher versions, at least in the .org, it will give you to which it will give basically some numbers over here that will give you a version of Ubuntu. So this one is compatible for Ubuntu 22.04. It is compatible with Ubuntu 24.04 as well. Okay. If I were to go to OpenFOAM 9, see over here for OpenFOAM 9, it will show that it is compatible with 18, 20, 21, and 22, and it is not compatible with 24. So if you ever install not OpenFOAM, but WSL version 24.04, you won't be able to install OpenFOAM 9. It will give you an error. So always when you're installing anything, check the very first lines whether it is compatible with the current version of Ubuntu. Okay. So just check these things. Same goes for the older versions of OpenFOAM, the basically OpenFOAM ESI versions. If you were to download OpenFOAM, say 1912 or 2012, you check whether they are compatible with your Ubuntu version as well. Otherwise, you will end up with errors and you won't be able to download it. Yeah. So this was the overview of how to download OpenFOAM and WSL. So see in the comment there are okay. Okay, if there are any problems, you can ask now since we have time. Till 4:30 we have time with the installation session. After that, we will start with the demonstration session. Okay, no problem. You can use it manually. Okay. Okay, so I think most of the issues are solved. Okay, so OpenFOAM ESI version sites were down. Paris has answered that. So in your email that you had received, there was also one link, one YouTube link. Now, that was set for OpenFOAM 2412. If you are downloading OpenFOAM 2506, that is the latest version, you can refer to that video because in that they have told you how to build it from the source. Because since there are company changes there, it is not downloading the normal way. So you'll have to build it from the source. Setting up alias. It says it can't identify OF9. Okay, so I'll show the bash RC. Mhm. Okay. So in your alias, have you specified properly with inverted commas and everything? Okay. And can you confirm whether your OpenFOAM 9 is installed properly? Because if your OpenFOAM 9 is not installed properly, it can't find this bash RC. This bash RC file for OpenFOAM 9 will only generate once your installation is done properly. Okay. Okay. So have you checked the for typos or anything else? So it's OPT OpenFOAM 9 etc where? Okay. Okay. Did you type basically any whether there's this code you've typed it over here outside before an alias? Because in the first sheet, if you see for OpenFOAM 9, we've told you to we've told you to add this line in your bash rc file. But in the second installation sheet, you don't have to write that file. Basically, you don't have to write that line in your file. You can delete that line and directly type over the alias OF9. Otherwise, it will always by default start with OpenFOAM 9. Okay. Is anyone facing any installation problems? So if you're facing any installation problems, you can unmute as well. We have time till 4:30.
Hello, sir.
Yes.
I missed the installation at the start.
Okay.
Now I'm following a YouTube video on YouTube. Uh, there I'm stuck in uh, the installation package of Ubuntu.
Okay. So you're still installing WSL, right?
Yes, sir.
Okay. So what exactly is the problem in that you're facing?
Sir, here it's after I paste the code of uh, OpenFOAM V3 V13.
Hmm.
Uh, I'm not able to get install the Ubuntu complete package. It's getting stopped at return to std out 1710 to 1710. That's
Okay.
it.
So you're trying to download V13.
Yes, sir.
Okay. So in V13, you're downloading it for Ubuntu only, right?
Yes, sir.
Okay. And your Ubuntu version is, have you checked it is with 2404 or it is any higher than that?
No, I haven't checked. It is 22.04.
2204. Okay. So these two commands, did you run them together or you run it separately?
Okay, yes, there are two commands. I run those with togetherly. I didn't
O-
make it.
Okay. So first, just try running them separately. Like you
Okay,
run this one first, then you run the second one, and
okay.
then go ahead with the whole thing. If that resolves the issue, then good.
Yes,
Because sometimes when you type both of them, it will only run one of them or it gives an error.
yes, sir. I'll try.
Yeah. And one, when you're copying also,
Yes,
just
sir.
check whether there are proper spaces and all.
Yes, sir.
Yeah. Yes, Teja, you can always ask ChatGPT as well. But sometimes when you try to run some commands from ChatGPT also, it gives you some command, but it not necessarily works. Okay. Is anyone else facing any issues while installing? Okay. If anyone is facing any issues, you can type it in the chat box or you can unmute yourself as well. Okay. So since I think most of the people are trying to install and most of you might have installed already. So we can go ahead with the demonstration session now. And if you have any queries, then we can take it up in the Q&A session at the end of the session. So in that you can have your question answers or anything related to the demonstration as well. Okay. So Pranay, you can go ahead with your very first demonstration session.
Just a second, one doubt.
Yes.
Sir, I mean, that doubt got resolved. I ran the two codes separately, got it. Here
Okay.
now, I have to run the code of this thing. OpenFOAM, that only upgrade OpenFOAM 13. You told that it is better to start with OpenFOAM 9 if we are beginners. So shall I just change the code, just change the number of 13 to 9? It will be okay.
Yes, because I think wait 1 minute, I'll just once check it. I think the command is exactly the same, only the number is different.
Yes, sir.
Yeah, so you have sudo basically apt-get -y install openfoam 9. Yeah, so it's the very same thing. You can just change the number from 13 to 9.
Yes, sir.
Yeah. Okay. Yeah, so Pranay, you can go ahead.
Sure, Ivan. Thank you.
Yeah,
I'll take 2 minutes time and I'll then start.
sure.
So until then, I want the audience to just put in the chat box how many of y'all have ever watched an F1 race or have an interest, keen interest towards the aerodynamics as a subject, or aerodynamics of a F1 car, of a car, of any other vehicle. Just drop in the chat box. Until then, I'll keep the case ready.
Okay, so Nived has an interest in F1. Anyone else? Okay, there are quite a few.
Hmm. Okay. Even if it's not F1, maybe you guys might have a keen interest towards aerodynamics, understanding the lift and the various aerodynamic parameters. So that goes to. Okay, I'll share my screen. Mhm. Okay. Yeah, is my screen visible, Ivan?
Not yet. Yeah,
How
it's
about
visible
now?
now.
Yeah. So first and foremost, let me welcome you all to the session. So as part of the first session, first demo session, we are going to see how a F1 car can be simulated in OpenFOAM. Uh, Here we are preferring a 3D model rather than the conventional 2D model. Uh, so first and foremost, let me show you the already set up case. Okay. So towards my left window pane, okay, under this Explorer section, I hope it is visible. Uh,
Can you increase
s-
the font size?
you want me to increase the font size? Okay. Okay. Yeah, done.
It's better.
Okay. So first and foremost thing, skip everything towards the right. We are not going to see any files. So let me take you through what we are going to do. In this case, let's begin with the README, or what you can say of F1. Okay, so this is the F1 car we all know. It is a very costly machine made for leisure purposes, and it is a engineering mammoth. And behind engineering, apart from various analysis we do, the structures, the aerodynamics, the controls, what defines the speed majorly apart from the engine is how you design it, how you shape it, how you control the forces over it. Okay, over, in, and around everything. Okay, so this is the visualization. This is the CAD model actually sourced from internet, and we all can do it the similar way. Um, First, the first method, the first thing what you do is, after sourcing a CAD model or after you draw a CAD model or a geometry, you move on to discretizing the domain. You move on to creating a domain, and then you discretize it, divide it into very fine elements. As you might have heard towards the beginning, ki what is CFD and all. So I wouldn't repeat much. So let me take you through what are the steps involved. So this case can be run on your system as it is already uploaded on our FOSSEE website. Towards the end of the session, we'll definitely share you the said case and all the instructions required to simulate and mimic the exact case on a system. Fine. So right now this is my terminal window. For many of you, since I'm using VS Code, it is quite different. Or do you want me to use the terminal itself?
Pranay,
Either thing works.
I think the
Yeah.
terminal will be better since they are beginners.
Okay, fine. I'll just zoom it then. It's visible, or should I increase the font much? Uh, okay. So okay. So right now we are in the case repository. Let me tell you, the current repository which when you download will show three files, three folders and one file. That is case folder, the report folder, the results folder, and a readme.txt or readme.txt for all of you to read before starting the simulation on how to go about it. So first and foremost, we'll enter the case folder. Okay. In the case folder, primarily there are three main folders, subfolders, known as CD, 0. This gives us the initial time step and what are the boundary condition at the very beginning. Okay. Ignore everything else you see on the screen. Then is the constant folder. This constant folder has thermophysical properties and the properties of the fluid in consideration. Okay. Yeah. As you can see, there are transport properties. These transport properties carry the information of the fluid. In our case, it is air. Turbulence properties is selecting the turbulence model. And then polymesh extended feature edge mesh tri-surface is all related to meshing purpose. That's you can ignore as of now. Then we move on to the systems folder. So in the systems, you will see mainly block mesh dictionary, control dictionary, and many such dictionaries. This dictionaries basically make your task easy, first and foremost part. Secondly, they set up the case, they set the simulation settings. Third, they define the mathematics behind the simulation. Okay. And then accordingly, we define the schemes required to resolve the results. If you need good results, of course you need to work very closely with the mesh part and the mathematical part. I assume many of you might have a good exposure of CFD and basic on engineering mathematics up to second or third year in numerical calculation. So that might give you a hint. So just let me show you what a block mesh dictionary or consists of. This block mesh dictionary is okay. Uh, I'm sorry. Okay. No system. Okay. So block mesh defines a very wide three-dimensional volume under which your geometry file will be there. Okay. So yes, this is the code with defined. It extends from minus 0. This for now, let's ignore this jargon and I'll move on to the next part. So similarly, each of the dictionaries has something or other things involved. To start the simulation, you have to execute the all run command. Okay. In your terminal, you have to first give the permission to make it executable. So what you do is chmod plus x, then you write a. It's okay if you're not getting the commands, I'll share you all. It's just for me how this simulation progresses is mandatory at this point. Okay. I'll show you the results. So all run permission has been given. and then I'll just write all run in my terminal using dot and slash. Okay. And then I click execute. What happens is, first and foremost, the mesh the mesh is getting created. Okay. Let me show you what all run consists of. Nano, all. So okay, see, if you can see this, it is sourcing the run functions, the functions in the OpenFOAM directory. It will be later useful to to reduce the tremendous task and to reduce the, to bring out more repeatability in the solutions and solving the thing. So first and foremost, this surface feature extract, we have to, since this is a CAD file, we have to extract the surface. Okay, the STL surface. So that is that command block mesh. We have to put that enclosure into a governing domain. I'll show you in the visually right now. Just I'm sh- I'm trying to emphasize on what exactly the all-run consists of. Third, we are just 0.org is 0.original. This is the original file. Original in the sense this is the main file, and I'll copy it and rename it as 0. So that becomes my first time step. The content is same. It's just I'm renaming it and preserving the original directory structure. Okay. The topo set once again defines the topology. Refine mesh further refines the mesh, increases the quality. Snappy hex mesh is a tool to mesh advanced geometries, complex geometries, very like manifolds, like advanced curvatures and all. This get application is calling the solver. In our case, it is simple form. And then we move on to paraform to visualize the results. Okay. Let me show you the mesh first and how it is. Okay. To open mesh, I just click type paraform in this format, uh, and then select enter, and then I go to apply. Okay. Once this is applied, never mind. I'll do it from the settings. Wait, something is wrong. Okay, never mind. Uh, just a minute, as I just re-entered every command. So my polymesh dictionary, which consisted mesh files, it just got reset it, and hence you saw that error. I have a different file, cd downloads. Okay. Let me show you. Yeah. So as of now, we are just going to see. So this is the enclosure which I was talking about. Inside this is the F1 car. Okay. To see it, we can just toggle it on. Okay. Okay. If you want to see how fine is the mesh over it, basically, if you guys know what mesh is, then let me tell you this simulation consists of 30 lakh cells. Okay. 30 lakh is a very huge number for computational time on a normal laptop. Okay, see how fine is this, and this cannot be achieved very easily unless you define very large number of parameters. Okay, So that's why we have to use something called a snappy hex mesh, then topo set dictionary and surface feature extracts, likewise and all. Okay. And the other boundary conditions, let me show you. Apply the front and back patches will come. Okay, this is the front and back patch. The inlet shows from where the air is entering inside the control volume. Okay, the lower wall, basically this is an enclosure, so we have to cover every side. Okay, please do take care of this. Similarly for upper wall and then for outlet. Okay, never mind. And then the outlet. Okay, and then what is, after mesh is created, what is the next set of commands that we give to execute it is, the mesh was created using some 3-4 commands, as you can see in the all run file over here. The first command was surface feature extract, block mesh, then topo set, refine mesh, and snappy hex. So this 5 commands are used to create the domain. Uh, firstly, the geometry, the domain, and then the mesh. Okay. After this comes solving part, solving the maths, solving the physics, and solving the aerodynamics of the actual motion. Okay, the current simulation relies on mark velocity of inlet velocity of 96 meter per second, almost 96 meter per second. That is close to 350 kilometer per hour. Okay, so that, as we all know, as this kind of flow is turbulent in nature, so hence we have to prefer some turbulent solving model, which is k omega in this case. uh, to solve it, we have to just we have to just write in the terminal our solver name, simple foam. Please do not see the terminal as of now, this is just a different format. Okay, uh, it's just a different layout. Write simple foam and it will start creating it. uh, okay, it is time. Since this case has already been solved, because to prevent computational time and loss of, and to adhere to timeline, I'll I'll show you how what the results look like. See, I'm just solving it for 30 to 35 seconds. It will take time because of 30 lakh cells, and first it reads the P and U file of the last time step, 30. In your case, if you're starting, it will read files from 0. Okay, and then it will continue solving it, and until you define a convergence criteria, that is what is the amount of residuals are okay to have in your system. It will stop there, or it will continue until the end time. Okay, so let me show the qualitative results first, quantitative results first, then I'll show you the visualizations and all. So first, and as many of you know, the prime coefficient to analyze all this thing is the CL versus CD graph. Okay, so this is a custom script devised exclusively for this, and this is the data which we got after solving the case. This is a CL versus CD graph, CL and CD versus time graph. Okay, on the y-axis, we can see the blue line denotes the CD at the very first time step, that is at 0.1 second. The CD is very high, 3.84. And as an aerodynamist, my hand, I wouldn't prefer a very high. That is, if somebody is pushing you with, uh, just imagine it this way. If somebody is applying a force of 1 Newton on you, you have to counter that force, you will have to apply 4 newtons of it. Okay, so this is that criteria, or also known as the coefficient, due to which the drag force or the lift force is amplified or decreased. Okay, so it is usually preferred to have a very less CD in aerodynamics, from the aerodynamics point of view. And CL, here it is negative for to enhance the downforce. Let me show you what downforce is. So primarily this is what the expected uh, quantitative value was supposed to be after solving it, the CD and the the CL values. There are five values. So 3.84 is at 0.1 second. After the simulation little stabilizes, CD drops to 1.22, then 0.50, and then it fluctuates and oscillates between 0.55, 0.55, 0.54. Mind me, this is not the industry standard, because of course 30 lakh cells is nothing from the industry. Cells of size billions, mind me, billions of with computational time of days and months are been done. So with which calculates this coefficients with great precision. Okay, but to go there, you have to start from somewhere, and this is that somewhere. Now let's come to the visualization part, the colorful part. To visualize things, you have to use parafoam command. You have to use the paraview tool, and to access it, you can either write paraview in your terminal or just write parafoam. Okay. Once again, it will open parafoam. You have to select apply. It will take time. It will take time. And to see different results, you'll have to manipulate things out here. You have to first cut the slice to view a particular section. Okay, if you want, we'll have to use sections to better understand how the flow is going in and around. So that is the cut section. Uh, as we are short of time, I'll show you how the contours are supposed to look like. Okay, so yeah, and one more thing, apart from zero constant and system, as the solver goes continuously solving the maths, and I have the liberty to log some data. And that data, as of now, uh, I preferred CLCD and the different aerodynamic coefficients out here. You can see it's neatly arranged. CD stands for coefficient of drag. CDF is this is three axis. CD along three axis. Okay. CL once again, CLF, CLR, and then CM pitch, CM roll, CM rule, CM yaw, and similarly CS. So as for plotting purposes, I consider only CD and CL. Okay. And that's the power of OpenFOAM. It's you can log data as and how much you want to, okay, without any restrictions and very in a very smooth manner. You just have to define functions in your control dictionary. Uh, that's the jargon. Let's skip that part. So let me show you the results. Okay. Mm, okay. So this is that diagram I initially told you. This is the car. When it goes with very high speed, there is almost up to 7 G force. Okay, 6 to 7 G force. Because of aerodynamic braking, the car is of 10 newtons. Assume it's a very layman figure. Just assume it is of 10 newtons. But with aerodynamics forces around cornering, it becomes 40 newtons. Okay, that is 400% amplification. And then again during braking, because you have to come from 350 kmph to zero within seconds. Second is a very big word. You have to be there within fractions. Okay, so that delta t is all accounted, and then you get almost 6 g of force. That is gravity acts 6 times if on as that of normal condition. Mm, okay, then this is the contours. This is the streamline of how the flow goes around this car. And then this is again the contour at different time step. Okay, this is at time step number 7, or when the simulation at 7 seconds. This is the flow visualization. Okay, if you can observe, the flow is where the flow is here. The flow breaks here. Okay, Then you can resolve different types of vortices, eddies, a different time step. This is note, we are not resolving temperature as of now, just for simplification purposes. And do also note this, we can analyze whatever we want, whether it is temperature, whether it is energy consumed, whether it is forces, whether it is different parameters, whether it is heat transfer rate, aerodynamic heating. All such capabilities are built in or can be built in, implemented using this software, and that is OpenFOAM. Okay, this is a real like okay, this is from the top view. Okay, this is how the velocity and the pressure contour is. Okay, this is for those people who prefer colors in life. Okay, who understands more using colors. I am that person who prefers understanding visually first, then I can prefer the numerical value. This is a cut section of how the mesh is across the entire domain and how it is uh, across the car. And once again, photo. This is a domain which I showed earlier. This is once again, you can ignore this. Ignore this. This is basic physics we all might be knowing. This is done. This is a streamlines. Resolving streamlines is once again computationally intensive. And for something of order of 30 lakh cells, it will take time. So already everything is processed and kept ready for you guys. This is once again, the enthusiasts might be knowing it very well. The front part of the F1. Then this is the mesh. Look at the pressure contours. At many point, you will also see in the domain varies from minus 1400, 1400 to plus 5000 pressure. There is negative pressure. There is positive pressure as well. Basically, pressure is not negative or positive. It's just the suction side and the opposite to suction side. Okay. This is the rear wing simulation showing the streamlines, how it is flowing. Residuals is the once in short, residuals is the difference in calculation obtained from. Okay, it is the slight numerical anomaly or the error accounted. Okay, nothing else. uh, and this is a cut section, the sectional plane with the mesh involved. So yeah, this was the results of solving on or understanding aerodynamic study of Formula F1 car using OpenFOAM. This case, once again, I would like to emphasize that you all can mimic this case using the commands. We have a very good documentation on how to execute things for every beginner. The readme text is there. If any doubts, please contact us. We'll be there. Yeah. So this is the quick summary or the quick readme. As and when you prefer to do it, there will be errors, there will be some up and downs, but do not pull yourself back. Okay, that is, every beginners is made to get stuck at some point to further grow. So that was more of a moral thing. Anyways, thank you. I hope something went in, something fed your curiosity of how OpenFOAM can be used. Yeah, Ivan, that was all from my side. Thank you.
Thank you, Pranay. So, Paris, you can go ahead.
Yes, Ivan. Uh, Thank you, Pranay. Wait a minute, I'll share my screen. I hope it is visible. Is it?
Yes, it is visible. So just an announcement, if you have any doubt from any of the sessions that are taken by Evan or Paris or Pranay, you can just write to us at contact-cfd@fossee.in. At that, towards the end of the session, I'll mention I mean, I'll just show you our website. There also I'll show you where is it. First, in the meantime, you just note it. I'm just keeping it for record in the chat box. Okay, so yeah, please continue, Paris.
Yes. Okay. So, very warm welcome to the students who are attending this pre-internship workshop. My name is Paris Palkar. I am the research assistant serving in the CFD Open team of FOSSEE, IIT Bombay. And for today's agenda is to demonstrate a heat transfer case study based on matrix cooling for gas turbine blades. So I would just like to thank Pranay for his demonstration on aerodynamic case studies. Now we will be moving towards heat transfer. The basic fluid is similar, but in heat transfer, our focus of interest is morely towards calculating the forces that are involved externally. For example, lift force, drag force, or we can calculate non-dimensional number such as coefficient of drag, coefficient of lift. However, in heat transfer, our main aim is to simulate conduction, convection, or radiation. These are the three modes of transfer, and we can plot some non-dimensional number such as Prandtl number, Nusselt number, etc., etc. Moving forward, so firstly, where you can find this case. So I'm linking this case website. You can just click on this website. It will directly make you to the FOSSEE's web page, where you can copy this matrix cooling for gas turbine blade. It is proposed by Mr. Jinu Chandra. Either you can download the abstract or you can download the whole case study to reproduce the results in your own system. Just to get a feel what we are doing, if you want to just understand what is being done, you can download the abstract. If you want to simulate everything from scratch, you can download the case study. A zip file will be downloaded in your system. You can extract it and make some changes as per your need. Okay, so this case study was proposed by Professor Himani Girl. She is the assistant professor at the University of Sweden. Along with that, Mr. Nikhil Chitnavis, who is a PhD scholar at IIT Madras and also a FOSSEE research associate, has contributed to this case. And they were working with Mr. Jinu Chandran, who is a research assistant at BITS Pilani. Our main objective of today's heat transfer case is to find the heat transfer characteristic with lattice work cooling structure operating in a turning flow configuration. So now you might be wondering what is a lattice cooling structure or why we are concerned about turning cooling structure. So previously, majorly the studies were carried out for the straight channel studies. Basically, lattice cooling configuration or straight lattice cooling configuration is used to trailing edge cooling application in gas turbines. The application domain is in gas turbines, nuclear system, or electronics. And here you can see there is a crisscross system arranged in a way so that the coolant can flow upwards and downwards. Here you can see there are two streams. This black border you can call it as sidewall, and the upper subchannel and lower subchannel consist of make a way through which the coolant flows. And with the combination of these two channels, a rib is formed. And here you can see the straight channel and how we can simulate straight channel at various angle. So right now the inlet flow angle is 136 degree and the outlet flow angle is 68 degree. Similarly, you can change the angle of attack and angle of incidence to optimize the heat transfer area and get the results done. Simulating with all run. So if you are a newbie to OpenFOAM, you don't know anything about OpenFOAM, all you can do is download the case file. There is a, let me show you through my terminal. I hope it is visible to all. Is it? Can anyone confirm me?
Yes, it is visible.
Yes, it is visible.
Okay. So if you download the zip file, here I have just simulated 3 cases, but you will be getting 5 cases. So what you can do is ls is just list out what is in the turbine cooling folder. Just list out what is in turbine cooling method. If I want to go in the case 1 folder, what I'll do is I'll do cd case, and if you hit tab, it will all on its own prompt you that the thing that you are interested in. So now I am in case 1. Now again I list out what is there in case 1. So there are various files that are present in this case 1. Let us understand one by one what are them. Initially, if you don't know anything, you can directly open the all run file, readme file. Here it is written to give executable permissions. You can run the script all run and all clean. To run the full simulation, you need to use this command. And to clean the simulation, to remove all the working directories, you have to run the all clean command. So let us try them. Now I'll do the all run.
Faris, could you please hold on for a few minutes, because from Deepak's side, no, from our e-studio, there is a power shutdown. So these
Okay.
things are not being recorded, but we need to record this. So
Sure.
just give me, say, a couple of minutes time. Let me see what can I do.
Sure, sure.
Yeah, please pause. I'll just come back to you.
Sure, sure, sure.
Paris, you can go ahead. I've started to record on my personal system.
Okay, okay. Share the screen. Is this screen visible?
Yes.
Okay. Yeah. So like I have used the all run script. So the first step was echo running block mesh and run application block mesh. So block mesh is a type of OpenFOAM utility that will create the background mesh for our snappy hex mesh, and to simulate our fluid problem. We can visualize it as well in the paraview part. I'll show it to you. I'll show that to you in some time. Next step is to run the surface feature extract. So what surface feature extract does is, if you are developing your own geometry in some another CAD modeling software, let's say FreeCAD or CATIA or anything, if you're using ANSYS Fluent, Space Claim, etc. So what you can do is you can directly export the .stl files, and you can directly place them into the try surface folder of your OpenFOAM OpenFOAM folder. Then what you can do is run the surface feature extract, and then OpenFOAM will try to capture the emesh file that are present here. It will try to capture the emesh file that are readable by OpenFOAM, and through which we can do our further refinement using Snappy Xmesh and run our case. Then the third thing is Snappy Xmesh override. Snappy Xmesh is a very complicated meshing directory. Again, it is provided by OpenFOAM itself. And the override command here states that key, whatever you have done previously in your Snappy Xmesh, just rewrite it again. Anything for our application, running the Snappy Xmesh could nearly take around for 1 to 2 hours. So I'm skipping that part. I have generated the mesh previously, so I'll show you using my presentation. Again, then there is an application called create patch override. Again, this override command is for the application that whatever you have written in the create patch command, erase it and write it again. And for create patch, we are using our custom patches. Let's say if you are naming your inlet in CAD modeling software, so this will capture it and it will name it inlet in the OpenFOAM. Check mesh is a application in which you can check the mesh, how good your mesh is, how well structured your mesh is. Let's try check mesh. Check mesh works here. As we are not working with this case, I'll run just check mesh. Now this will run. Just for your information, this is a very coarser mesh. The cell elements are near around 2.1 million, that is 21 lakhs, 91% of which are hexahedral, and the skewness index is near around 60%. That might cause some troubles in the conversions in future. So here you can see the total number of cells is 21,45,465. Okay, and if you want to visualize it, what you can do is there is an inbuilt utility provided by the ESI version, check mesh, right? If you write right, then this will give you some information key what you can do. Just hit tab, it will give you further information about it. So I'll just write all fields. Now it will write everything from scratch so that you can visualize it in your paraview. It is happening, just a minute. Now this is writing non-orthogonality angle, phase interpolation, phase skewness, and everything will be written into a file in your paraview. It has ended. Now the check mesh command has already executed successfully. Now what we have to do is we have to run our solver. For that, we will move further and I'll tell you how to run that as well. This is the all clean script. If you want to delete everything like what we have run previously, let's say the check mesh or snappy X mesh or block mesh, if you want to erase everything from scratch, you can just do all clean and it will clean everything that was existing in your folder. There are steps what is being executed one by one. If you write back dot forward slash all clean, first it will remove all the time directories that were present, then it will remove the mesh, then it will remove the log files, then it will remove the post-processing folders, and then it will remove the e-meshes that were provided by surface feature extract. While running the all run and all clean script, you can see a somehow similar window. Running this would nearly take around 8 hours. It took me 8 hours to simulate this. So I've just given you an idea what you should expect when you are running this case. So now we are moving towards the turning flow configuration. This geometry is proposed by Professor Himani, and this is used for trailing edge cooling application. And this is the inlet, and these are our ribs that we have discussed earlier. So when fluid enters from this inlet, it goes significant directional changes before going into the lattice work region. So you might be now wondering what is the lattice work region. Lattice work region is the region where upper stream and lower stream ribs are connected. So if you are able to see this section, it is known as the lattice work region. So this is the geometry and mesh discussion that we will be doing further. This is our inlet. This is a velocity type inlet. This is the lattice work region. If you are able to see, these are walls. Note that these are adiabatic walls, meaning there is no heat transfer occurring, and this is a pressure based outlet. Okay. The rim has a thickness of 4 mm. The height of rib is 10 mm. The inlet hydraulic diameter is near around 10 mm. The lattice section, that is this, it is around 265 into 85 mm. The beta angle is the angle of incidence that is occurring with the wall. This angle is 35 degree, and there are the channels are experiencing two angles in the inlet velocity. I'll show you what are those. For the downward angle, the angle is 145, and for the upward flow, the angle is 135. So let me show you. If you are able to see, there is a fine line that is separating our upper channel with lower channel. So the flow that is means the upward channel is facing the flow at the angle of 35 degree, whereas the downward channel is facing the flow at the angle of 145 degree. Now come towards the meshing part. Mind you, this is a very coarser mesh. I'm repeating this again and again because the grid independent study have not been carried out as of now. We can see the surface. This is the mesh, what it looks like. And if you want to see how the internal meshing is done, you can just go on this command. It is called slice. On the upper ribbon, upper left ribbon, you can take a slice in the z normal direction, that is normal to your flow, and you can hit apply. I have already that. It will take computational power, so I'm avoiding it. You can use solid color, and you can use surface with edges, so that it demonstrates you how the boundary layers have been formed here. So you can just twinklet it and see it very deeper way. So this is the boundary layers that are being formed, and this is the near view of the ribs. The total mesh count is 2.1 million, and out of which 91% of these cells are hexagonal. These are some boundary conditions that we are using for the simulation. For velocity, we are using fixed value, zero gradient, and for outlet. And for walls, we are using no slip. If you want to know more about this, you can directly go to our spoken tutorials website. You can find everything about this. What is boundary? Why this boundary condition is used for particular case in detail in those tutorials. I'll skip that due to time constraints. Turbulence modeling. In turbulence modeling, we are going with the SST-K omega turbulence model to resolve the near wall behavior of the fluid and to capture accurate vortex structure. A dedicated turbulence modeling demonstration tutorial is in the line that will be provided by our FOSSEE research assistant. So kindly stay tuned for that. For now, we are using the buoyant bossing simple foam. It is used for steady and incompressible flow solver. And buoyant bossing simple foam generally works on the bossing approximation to model the density changes that arise due to the temperature. And this solver solves continuity, energy, and momentum. Only there is one thing, that in momentum equation, a body forcing term is introduced to calculate the bossing approximation. It is generally used to simulate natural or forced convection in your CFD simulation. So now let's go to the results and discussion. This is the temperature plot for mass flow rate of 0.0139 kgs per second, and you can see the temperature distribution in this. This is for another parameter, that is 0.0404 kg per second. For this plot, I have extracted the temperature plot as well as the velocity plot. This is taken from the upper stream of the view. So the angle of attack with the fluid was 35 degree. This is the temperature plot, and this is the velocity plot. Now let's come to basic results and discussion. So here we can see that the pressure loss is increasing in the lattice work region as we increase the mass flow rate, and the change in pressure shows a non-linear trend for Reynolds number that indicates we are having some viscous losses and flow separation occurring near boundaries with higher velocities. Also, this is a coarser mesh, and if we refine our mesh more further and further, we will tend to get same physical results with more accuracy. And these are this is Nusselt number that has been plotted, and again the Nusselt number is also increasing as we increase the mass flow rate, and the increment is not uniform in both channel, upstream and downstream, upward section and downward section. As for the upward section, upper sub channel, the flow is showing more chaotic in nature, and it is not aligned with the flow. You can plot your results in this. You can take a slice, then you can go on the temperature parameter and turn on the surface. So this is for 100 second. This simulation has been carried out for 1000 second, and this is what temperature contour looks at for time is equal to 100 seconds. Similarly, you can simulate you can visualize velocity as well. For again, this is for t is equal to 100 second as well, and there are various factors, that is k, alpha t, nut, omega, pressure. In this uh, in this region from inlet, you can see there is a from legend you can see there is high pressure region and it is low pressure region. So as the time will progress till 1000, the air will go from the high pressure region to low pressure region, and the air or the pressure in this system will be neutralized. uh, and yeah, that's all. You can simulate this case with very more accuracy as well, but due to time constraints, I'm skipping more explanation part. If you have anything else, just put the comments questions in the comment box. Me and the team will definitely get back to you in the Q&A session. That's all from my end. You can continue now, Manjil Bhaiya and Ivan Bhaiya. Thank you.
Yeah, thank you, Paris. So now we'll just go ahead with the multi-phase flow. Yeah, I hope my screen is visible.
Yes.
Oh, so for the multi-phase flow, you can go to our site, you can go to case study project and completed case study. In this case, we'll go down to case number 131. Yeah. So we have this simulation, multi-phase simulation using OpenFOAM, using basically to calculate the ship hull resistance. Okay. So I'll show you the case file. Okay. So this is the report. It is by Rishabh Sharma from IIT Madras. So in this, what they've done is he's calculated the ship's hull resistance, that is the force acting on the ship's hull. So I'll show you the CAD file there. So this is the hull he has simulated over, and we have a multi-phase flow acting. So you will have two types of fluids. You'll have one gas phase and you will have one fluid phase. So you'll have two of these phases, and basically he's only calculated the fluid phase acting on this object, and then he's compared the data, that is your force resistance, with various basically with different methods. So if you scroll down in his report, you will find that he has compared the whole result with three methods. One was your Eulerian method. Other one is with Crank-Nicholson method. So I'll show you the files itself. So once you download the file, you will have it in a zip file. You can extract that. Within that, you will have again another zip file. You can open that. Yeah. So he has compared these four types. One is the Eulerian approach. The other one is the Crank-Nicholson one. Then he has done an basically a local Euler interface one and one with an MPLIC one. So for our case, we won't demonstrate all four. I'll just show you how to run one case, say for Euler. So I've already copied this into my run directory for 2412, as you can see. So yeah, so I will before opening any of these cases, you should always read the README file, because whether it is multi-phase or any other type of flow simulation that you're trying to see, it's always advisable to read the README file, because in that they usually explain how to run the case properly. Otherwise, you might run it in a way that it is not implemented to and you'll get errors. So in this one, he said that Crank-Nicholson Euler and local Euler interface, they can be run with OpenFOAM 2112. So we are using 24, so it will still work. And the local Euler MPLIC, he's run it with OpenFOAM 9. So if we were to just directly randomly run any case, we wouldn't know this. So it's always advisable to open these files. Then he's told that we have an all solve file that solves everything. You have the all run that only solves for the mesh. The all mesh creates the mesh, and then you have foam clean to clean the tutorial. So enough with this. So let's open the Euler file. So as he was saying that you have the all mesh, all plot, all run, all solve. So as he said that the all solve file will basically do everything. So in this, he said that it is running the all run case and he's doing the all mesh. Okay. 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 I hope my screen is still visible. Okay.
Yes, you are.
Yeah. Okay. So in multi-phase, as I said, you would have a gas phase and you would have a liquid phase or or a fluid. So how do you set up case for such things? Now you've seen for heat transfer and for aerodynamics, it's very simple since you have just one phase. You just have air and everything is happening within that medium. But for multi-phase, you have to go about certain things that will help you execute it properly. So the very first thing is you would have additional boundary conditions. In this case, we have alpha dot water. So in this, we will initialize the, okay, yeah. So in this, we will initialize or we'll set up the boundary conditions for that water itself. So in this case, we have inlet, outlet, atmosphere, and then we have boat. And also the mesh is created in SnappyHex. Now, since we've seen already two cases in which they've used SnappyHex mesh, so I won't go too much into that. Similarly, in your transport properties, unlike before, you would only have, say, just the transport properties for air, that you would just specify the kinematic density. Whereas over here in multi-phase, you will have phases. So over here, you'll have phase, water, air, and then you will basically set up the parameters or the fluid properties and the air properties for both of these. So you'll have for water and for air, and then you'll have sigma, that is your surface tension. So I'll show you what exactly we're trying to simulate. I already have this simulation run. So I'll open it in Parafoam. Yeah. So this is our domain in which we have the fluid and this and the air on top. So just turn the opposite. Wait, first we'll generate the boat. Okay. Yeah. So you can see that there's a boat inside. Okay. Over here. That is the hull of the ship. So if I click on alpha.water and I go to the very last time step, now I've run it only for 20 seconds, whereas the actual case that the intern has ran it was for 60 seconds. So if I show you the top, yeah. So if you see, as the simulation progresses, your flow will be something like this. It's also shown in the report. So you will have something like this. So in this whole simulation, he's calculating how much force is acting on this object, and he's plotted that force and he's compared that with the four various techniques that he's applied. Okay. So this is the whole idea of this case study. So to run this case study, you would first have to open it in your terminal. So now since I've right clicked and directly opened it, I'll type WSL to basically enter my Linux environment, and then I'll type OF2412. Okay. So once this is done, first you can directly start with bash all solve. Since he said that all solve will just run every single thing, so we'll go with all solve. So as you, okay, I'll show you the all solve. In that we had all run and all mesh. So let's go with all mesh first. In all mesh, you have a set of commands that will be executed. So first you have rm and then you have 0.o, basically 0.alpha water. So what this does is it will remove any old files of alpha.water that was there. So if you've noticed in the 0 folder, we had just alpha.water.org. So in a multi-phase simulation, whenever you're simulating anything like this with any of the water parameter, we always save it as an org file and then we copy it just before running the simulation. You will copy this org file and you'll rename it to alpha.water. So why we do this is if I were to open this file, you'll see that OpenFOAM, when it is running any simulation, it will start overwriting this file. So if I were to run this case with just alpha.water and then it will overwrite the file. And then later on, if I find out that my simulation is not correct and I want to make changes, I would have to scroll down or clean this entire file and then again start. So that's why it's advisable to save most of your files in a .org file. And just before the simulation, you copy it and just rename it to the alpha.water file. Then you have foam clean tutorials. What this command will do is it will just clean up the whole command, like if clean up your whole case. So if you run the simulation and you have some basically you'll have some old files that you've run. It will clean all of that and it will give you a whole fresh case that will only have your zero, constant, system, those folders. Then we have make directory 0. This is all for snappy hex. From here on out, it will start with snappy hex. Since we've made the mesh in snappy hex, so it will start with your surface extract, then it will create a block mesh, then we'll go ahead with distributing the whole thing. Now in our case, since we ran this case, it will give me an error. Yeah, so you see it's given me an error. So before you run any of these simulations, it's always better to open these all run all clean files. Now in my laptop, I only have say 6 cores. And over here, I am basically running this whole case decomposed. But in decomposition, they have specified over here 80 cores. Now my system does not have 80. So I would have to obviously change this to say 4 because 6 is the limit. I'll always keep say 2 cores empty to do some additional work. So I'll save this with 4 and then I open the all run file since these are the 2 files that are running. Now your all mesh will create the mesh and your all run will run the whole simulation. So again, it's clearing all the previous alpha.water files that was created. It is removing any previous processor. If you've decomposed it, you'll get some additional files and any post-processing files. Then you have the set fields. And again, before that, before explaining set fields, I'll just change all of these to 4 so that we don't run into any errors. Yeah. So once this is done, save. The set fields is where you will basically distribute your block mesh. Now in your block mesh, you're just creating a whole domain. Okay. In your block mesh, you're just creating a whole domain. So what the set fields is doing is, I'll open the file. Wait. You'll have set fields in your system. Then you have your set fields dict. Okay. So in the set fields, we specify a region or a box that we want. Basically, we want to specify anything inside this box to behave as the fluid. So we have specified a start point that is your higher limit and your lower limit in 3D space. So once you specify this box that is in simple terms written over your box to cell. So any cells that are within this coordinate system, we are saying that this volume is your water. This is how you will define multiple phases. So if you've seen the bubble column or any of our previous workshops in that we had demonstrated how to simulate a bubble rising. So similar cases like that, you have to always use set fields to specify a number of cells to behave in a particular way that you want. That is how you will specify your two phase or your multi-phase. Similarly, a box to phase over here. So here is where you will basically, it allows you to put a patch on it. So again, once you've done all run, it will run set fields, it will distribute, or it will break the whole uh, basically it will distribute a domain into smaller sets so that it can run faster. That's the whole point of decomposing your whole domain. Then you will run renumber. This one is not particularly necessary, but they've still put it. Okay. And then you run your actual solver. In this case, it is InterFOAM. So InterFOAM is specifically designed to run your multi-phase solutions. You also have multiple different, this you have two-phase Euler foam and many other. So you can always check that in the tutorial files under the multi-phase category. Okay. So once you've run this simulation, you will get some data like this. Now, as I said, he's comparing the force, but how are you to compute any of these forces and all? Because you are just getting you're getting some data, but you don't know how to use it, or you're not able to propose process it. So you can do that in ParaView itself. There are multiple ways you can extract that data, plot it over here itself, or the next most simplest thing in OpenFOAM, since it's open source and you can use Python and everything in it. So if you were to open the code, open any of this thing, he has a plot file that is a Python code. So if you open this Python code, in this he's written a simple Python code to plot all the post-processing data that he's got. Okay. So in post-processing, once you run the simulation, see, this is the run simulation. Okay. So once you run, you'll get some additional files. These are your time step files that you get. And since I've decomposed it, these are your decomposed files. That is on 5 processors, I've ran the simulation and then I've reconstructed it. Along with that, it will also give you a post-processing file. In this, you have your forces and you have all the forces files. So if I were to open this forces.dat, it will give me all the forces in all the 3 axes. Okay. Now, if you want to plot something like this, you can use always Python, or you can extract the data in ParaView and plot it accordingly. Now in Python, he's done a simple code, got the values, he's put that in the all plot. Okay. Now, since we've run this case, I'll show it in this one. So if I do bash all plot, so you see over here, it is giving me all the force data that it has calculated, and it is just plotting it into a simple GNU plot. So yeah, so you can close this, or you can just directly close the terminal. So this is the very quick way of running a simulation. At least for multi-phase, this is the most quick way, because multi-phase as in itself, it is really complex. And in the given time, you can't really explain every single thing. But in our previous workshops, we have explained in detail how can you set up a multi-phase case. But this whole session that we have is to show you that we have multiple cases that are already available. So you don't necessarily need to run, or you don't necessarily need to create your case from scratch. You can, suppose you have heat transfer or you have multi-phase and you just want to run something within the least amount of time. You just want to modify your geometry, say. So you can just download this file, change the geometry file that you have. Suppose you have, instead of a ship hull, you have a cylinder that you want to simulate. You can put that HTL file and you can generate your snappy hex for that cylinder and put it into this same thing with the same boundary names, and you can simulate the whole thing. So that is the whole point. So in this way, you can run the simulation, and if you have any more doubts in what exactly is going on, what boundary conditions he is used for each of those, you can go through these reports, because these reports are very detailed on what exactly is happening in the simulation. So in this case, he's put for inlet, for the velocity, he's put all these parameters. You also have for the turbulence model over here. So more about this turbulence modeling, Manzil will explain. So don't worry about that. And see over here, as I was saying, using the set fields dict, he has specified the lower end of the domain to act as a fluid and the upper end to act as the atmosphere. So this is how you differentiate between both of these, you can say, zones. And the ship hull is in the middle. So this way you can run a multi-phase simulation. If you have more doubts, you can always refer to these. Also, he's shown how to calculate all the results and all, how he's used it, how much error he's got between all of the 3 methods. Yeah. So this is a way to run a multi-phase case. This was just a brief intro on multi-phase, because obviously for the screening task, you won't be running any multi-phase simulations. it is a single phase only. But in case you are selected for an internship and you have to run some multi-phase simulation, so you can always download these case studies and you can always refer to them because they are more detailed as compared to the tutorial files that are already present in the OpenFOAM tutorials folders. And you also have a report and everything that is explained in it. So yes, this is the whole point of the multi-phase thing. Yeah. So Manzil, you can go ahead with the uh, dynamic meshing and turbulence modeling.
Okay, and thank you.
Yes.
Let me share my screen first. So I hope my screen is visible.
Yes, Mangal.
Yes.
Okay, welcome you all to the basic level CFD workshop in OpenFOAM. So this tutorial is aimed to be a beginner's level training session, and this tutorials will be demonstrated in the foundation version of OpenFOAM, that is the ORG version, and the version we will be using is version 9. So please feel free to post your queries in the chat. So the basic outline of this session is that we will be simulating 2D laminar flow in a channel, and then we'll also be simulating the 2D turbulent flow in a channel. So the problem definition is to set up a case for laminar flow through a channel, and after that we will be looking at how to set up a case for turbulent flow through a channel using KF model. And we will also post-process some of the results in ParaView if time permits. So this is the basic case structure of our case, which was also previously explained by other colleagues of my colleagues. So I won't be diving deep into this case structure or the folder structure. So the zero contains the boundary conditions, the initial and the boundary conditions. The constant contains the like the physical properties, transfer properties, and turbulent properties files. And the system will contain the control dict, block mesh dict, FV schemes, and these FV solutions. These are the settings, like the we assign the settings of our simulation in the system folder. The layout or the files are similar to the previous cases that have been demonstrated. Okay, so first we will be simulating a 2D laminar flow in a channel. So this is our channel that is shown in the figure. So we have the inlet, outlet, upper one and lower wall as boundaries, and front and back as a empty boundary as empty, because we are doing the 2D simulation. And the Reynolds number that we have chosen for our laminar flow is 500. So our average velocity at the inlet is 0.005 meter per second. So if you input these values in the Reynolds number formula, then you get the Reynolds number as 500. So basically, this is the kinematic viscosity, which is the value of 1 minus 5 meter square per second. So before running our case, I'll let you know where these cases are available and where you can download it from. So if you go to the FOSSEE website, that's cfd.fossee.in. So you can see that there are spoken tutorials available in this website. So if you go to the spoken tutorials, so you can see that you can access the OpenFOAM spoken tutorials from the CFD website as well. So first of all, there are many tutorials. So for the beginners, it is very this site is very good reference to start with. So they have started they are demonstrated for the how to set up the simple cases. So this case is also a simple case for the 2D channel geometry and mesh. So you can see in this, if you go inside to this then you can see that there is a video available to how to create a 2D channel geometry and mesh. So you can go to this video. And the other good thing about this site is that there are also the code files available. So you can download the code files as well from these. You can see in the right hand side, you can see there are the code files, and there are slides, and also we have the additional reading materials for each and every cases which needs uh, which needs another reference for the cases to understand the theoretical part. So there is an additional reading material as well. So first of all, I will not dive deep into how to create a simple mesh. So you can check these videos, and there is also another video on how to simulate a 2D turbulent flow in a channel using OpenFOAM. So there are basically two uh, links. So this one is one, and the other turbulence modeling in OpenFOAM. This is the other link. So the video is very detailed, and the more detailed is the additional reading material. So you can access this additional reading material from these sites as well. Okay. So now let's look at our case setup. So first of all, let's see look at the laminar flow for the Reynolds number 500 case. So I have already run the case in my system. So let's first look at. I want to explain the contradict FV schemes and FV solution, because this has been already been explained by in the previous demonstrations. So I'll give a brief overview in the block mesh. So block mesh, we have a structured hexahedral uniform meshing. So simple grading we have applied, and we have a 75 number of cells in the X, 30 in Y, and one in the Z direction. The one in the Z direction due to the 2D due to our 2D simulation, because we are running a 2D simulation, so we don't want any more number of cells in the Z direction. And also for 2D simulation, we need to keep the front and back as empty. This is our block mesh, which will create the generate our mesh. So after that, in the control dict, we can see that which solvers we have used. So we have used the simple boom solver, which is a steady state incompressible flow solver for laminar as well as turbulent flow. So we have run for the so in the simple form, this time is not important. This just refers to at the pseudo time. So because in simple form it is a steady state solver, so actually there is no importance of time step here. Okay, so I have already run the laminar case. So let's look at the boundary condition now. So as I have already shown in my slide, that the Reynolds number is 500. So we have velocity average at 0.005, which I have used here. And for the pressure, the boundary conditions are like the zero gradient, fixed value. So you can always refer to what this means after these after this demonstration also. And the other important thing is that these transport properties and the turbulence properties. So if you see these transport and turbulence properties, so in the turbulence properties, you define which turbulent model to use. So in our case, we are using the first case, we are using the laminar turbulence model, and the transfer properties is where you set your physical properties of the flow, that is like the turbulent, like the kinematic viscosity, that is new. So we have used 1e minus 0.5, which was also in the slide shown. So these are the basic files to set up our case and the basic inputs that we need to put in our files to run our case. So after these are set up, then we have a separate script called the all run script. So in the all run script, you type all the commands that you need to run to run your case or to run the simulation. So first we will be running the block mesh, which will generate our mesh, and after that we need to run our solver, which is simple form. So if you use the parallel processing, then you can also there will be additional commands like the decompose par and MPI run commands. So in our case, I have just used the serial processing, so there is no such parallel processing commands in my all run files. So this will be executed one after another automatically. So we do not need to type each and every command in our terminal. So this script will automatically run the. So let me see on my file. So I've already run the case, so I will not be running the case again due to the time constraint, and this will require more time to run. So in order to run the all run script, you just need to type // and all run. So if you after you type this command and then hit enter, then
Can you increase the font size?
then the commands in the all run script will be executed automatically. So you just need to type this and hit and press enter. So right now my cases are run. So before processing, let me show you how to set up a case for turbulent flow also as well. So before we set up the case for the turbulent flow, you need to have a good idea on what the turbulence, how to model the turbulence, or what parameters are required to model the turbulent flow. So there is a very good reading material as I've already shown you. So you please go through this reading material before you. This is a very good starting point if you are new to the turbulence modeling. So they have the very detailed calculation and detailed explanation of how we need to model the turbulent flow parameters like the y plus values, and for what value of y plus we need to assign the gradings. So because in the turbulent flow y plus is very important. So near the walls, if you are resolving the viscous sob layer, then the y plus should be very less than 1. Similarly, if you are going over y plus of 100, then we need to use the log layer approximation. That is, when we go to the log layer region, you need to use wall functions and all these things. You can refer to this document. There is a very detailed explanation, and all these values, how do you calculate these values? The numerical values are also calculated and shown here. So I have also used these values in my cases. So if you look at the turbulent case, so let's see at the turbulent case using K epsilon model. Okay, using K epsilon model. So this is the case. So if you look at the boundary conditions for all the K epsilon, so K is the turbulent kinetic energy, epsilon is the dissipation rate, and nu T is the eddy viscosity. So P and U are the boundary conditions for pressure and velocity. So if you see that inside the epsilon file, so you can see that I have assigned this value of 0.61. But if you want to know how to calculate this value, then you can refer to this document. So you can see that how the calculations are made as shown here. Similarly, for omega, for K, all the calculations are shown here. So I won't dive deeper into these calculations. And these are the boundary conditions. So we have for the inlet, we have used the assign the internal field of 0.61 as well. So for the outlet, zero gradient for also, and we have used, and the most important thing to notice is we are using K epsilon model, that is the high Reynolds number formulation. So K epsilon model, we need to, if you use K epsilon model and the y plus is greater than 30, then we should use the wall function to model the logarithmic change of velocity with the height from the wall. So the wall function will accommodate because when y plus is very greater or greater than 30, then we cannot resolve the viscous sob layer properly. So so if when we cannot resolve that viscous sob layer, then we need to use wall functions, so that these wall functions will automatically accommodate for that viscous sob layer which we have not resolved. So you can look or you can see how the wall functions works for different. So basically, wall functions are used for the K epsilon model, and K omega model is basically suited for the that is for the low RE formulation when the y plus is less than 1. So it is near the walls. So K omega model is best suited for in that cases. And also there are various advantages and disadvantages of these two models, which you can see on your own. Okay, these are the boundary conditions. So you can for the turbulent case. So this is turbulent. So basically, explaining what is Rans model. So Rans means Reynolds average Navier-Stokes equation. So we average the Navier-Stokes equation, which gives the fluctuating terms as well. That is the Reynolds stress terms, and the Reynolds stress terms need to be represented as the in terms of the average terms. So in order to represent that Reynolds stress terms in terms of the average terms, we use the help of the eddy viscosity models. So this is a class of turbulence modeling. And under the eddy viscosity models also there are K epsilon model, K omega model, and K omega SST model, which have their own advantages. So so if you want to simulate a flow that is highly turbulent and the separation effect is not present, or the adverse pressure gradient is not present, then you can go on with the K epsilon model. But if there is a high adverse pressure gradient, or the separation phenomenon is very prominent, then we can then K omega model is best suited near the wall regions. And the K omega SST model is the blend of these two models. So it uses K omega model near the walls, and away from the walls when the flow is more turbulent, it will use the K epsilon model using the blending functions. So yeah, that's basic of the Reynolds average Navier-Stokes equations. Okay, for these are the input parameters for our turbulent flow. So this we are using K epsilon model, and we are we are simulating for the Reynolds number of 2 into 10 to the power 6, and which gives us average velocity of 20 meter per second and kinematic viscosity of 1e minus 5. So, and we are using y plus of 200. So this is a very large value of y plus and lies in the log law region. Now, since we are using the since we are using the y plus of 200, so we need to also ensure that our first cell height lies in that y plus region. So to ensure that our first cell height lies in the y plus region, we need to calculate what our first cell height should be. So the calculation of the first cell height is provided in that reference document, so you can go and see that. And after that, it has also showed how to calculate this expansion ratio. So near the walls, the mesh should be very fine, and then coarser towards the center, because we want to resolve the that the wall effect, that is that it may be the separation point or adverse pressure gradient is prominent at the walls. So we want to resolve that very correctly. So this is important. So after this, then let's see the post-processing part. So if you type Paraform built-in, then this will launch the Paraform. Okay, this is our case for the turbulent case. Now we can also import the same. We can also import our laminar case in the same Paraform. So let us see. Let us import both these cases. Okay, so these. Okay, so these are the two cases, that is for the for turbulent as well as and the laminar case. So if you want to plot a velocity along the along a cross section in this channel, so if you can see what will be the difference observed between the laminar flow and the turbulent flow of our boundary layer. So you can untick and select only which is required. So let's just see the UX, that velocity in the X direction. So this is for the turbulent case. So you can see. Okay. Okay, so this is a turbulent case. Now let us plot for the laminar case also. So you can see that the velocity profile for the laminar case is this velocity profile, and for the velocity profile for the turbulent case is more flattened. So as we have also studied that the turbulent boundary layer will be more flattened than laminar boundary layer. So you can observe also from these simulations. So these are the quantitative analysis that we can do from this type of simulations. So if you also you can also see how different turbulent model will behave. Like I have only run for the K epsilon case, so you can also run for the Q omega case and compare between these models. So yeah, you can also see, apart from the velocity, you can also plot like the different other parameters like the epsilon. So you can see the epsilon is the highest at near the walls, because that in that region still there is laminar viscosity that is due to the viscous sublayer, and in those areas the dissipation of the turbulent kinetic energy will take place. So basically the ADs will be converted into heat energy. So we can see that there is a high dissipation near the walls. Also we can plot for the K, that is the turbulent kinetic energy. Turbulent kinetic energy is also minimum and increases. So only at the walls it is quite minimum than at near the walls. So the minimum is caused due to the dissipation of the kinetic energy. So yeah, in this way you can plot different values. So nu t is the eddy viscosity. So eddy viscosity, because the flow will be turbulent more at the center. So you can see that toward the center there is the value is higher than at the walls, because at the walls there is no presence of eddy viscosity, because it is the place where laminar viscosity will be dominating. So yeah, in this way you can compare between the different types of turbulent models, that laminar model, Q epsilon model, or Q omega model as well. So this is for for these two turbulence modeling. So as I've already said, that due to time limitation we cannot go detailedly onto all these values and all these parameters. So you can please refer to this document. This is a very good reference for you all. So let's move on to the next case setup. So the next case setup is the laminar flow over an oscillating cylinder. So these are the parameters. So we will be simulating a transient incompressible laminar flow across an oscillating cylinder. So we will be simulating for Reynolds number of 200, which is the laminar regime, and the diameter of the cylinder is 1 meters, and we have velocity of 2 meter per second. The oscillating amplitude is 0.5 meters, so the amplitude of oscillation, and the frequency is 0.5 hertz. We can also represent this amplitude and frequency in terms of non-dimensional values, like the reduced frequency and the non-dimensional amplitude as well. So in papers, in literatures, we will find mostly the reduced frequency and non-dimensional amplitude H. So, but for our simplicity, I have used these dimensional parameters in these slides and in the cases also. So you can see the boundaries we can see the boundaries. So we have the inlet, we have the outlet, top and bottom, and front and back is still empty because we are doing a 2D simulation. And the velocity at the inlet is 2 meter per second. Okay, so this is our case structure. So now the case structure is different, slightly different than the previous case structures. So I have highlighted here. We have additional files in our folders, like in the boundary condition folders, we will have a separate file for the point displacement where we will assign the dynamic mesh dynamic parameters, and we also will have a file called the dynamic mesh dict in our constant folder. So in this dynamic mesh dict, we will assign which solvers do we use for dynamic meshing, and so yeah, the solvers that we will be using for dynamic meshing should be assigned in the dynamic mesh dict, and the parameters of our motion of our movement will be assigned in the point displacement file. So we will be choosing turbulent model as laminar, and we'll be using a morphing mesh dynamic meshing strategy. So there are different dynamic meshing strategies available in OpenFOAM, like the morphing mesh, adaptive mesh interface, adaptive mesh refinement, overset mesh. So these are the various dynamic meshing strategies. But now in our case, we'll be using morphing mesh. So morphing mesh means there is a physical distortion or the physical deformation of the mesh. So we can see that our mesh is moving, uh, like the AMR case where the mesh is split into many more meshes, that it gets refined into smaller cells, smaller meshes. But in the morphing mesh, the mesh will deform and distort as the boundary moves. So this is but this also has disadvantages for like the large deformation or the large displacement boundaries. So if the displacement of the boundary, that the oscillation or the plunging or the pitching is more, then this might lead to divergence problems, and we need to monitor the current number and time step very carefully for these cases, for the cases of morphing mesh. Okay, so now let's look in our case structure. Okay, now I will show you first how to download, where did I download this case from. So if you go to our FOSSEE case study repository, and you can see the case study project, so under completed case studies. So if you go to number 44 case study, in the 44th case study, you see that there is a case study for laminar flow corrosion oscillating cylinder. So you can download this case study first. So I have already downloaded in my system. So let me show you that there are some changes that needs to be made, because these case studies have been run in the very older versions, and in the newer versions there might be some keyword errors, like it asks for new keywords and new syntax. So you need to look at those errors and debug it on your own. So let me show one such case. Like somebody had also asked, like if I have installed if I have installed OpenFOAM 13, then if does it run in OpenFOAM 9? So that might not run, because and throw some errors, because uh, this there because in the newer version that there might be changes in the syntax and keywords. Okay. And while we keep our rename when we rename our file, we should not keep any spaces in between our files, in between our words. So if you keep spaces, then that will throw errors. Okay, so after you download this and after you extract this, you can go inside of it. So you can see that there is a folder called case files, and we can observe that in the case files there is a space between the case and the files word. So this will also create the error. So you need to first remove this space. Now and this inside it there is no any all run file because these are the previous older cases. So I think the all run files are missing. But in the newest newer case studies, we can all find the all run all clean files and readme files. So you can see that it says the cannot file this cannot find file system block message. So in the previous structure, you can see that uh, the block mesh dict is inside the constant folder inside polymesh. But in the newer in the version higher versions, we need this block mesh dict in the system folders. So we need to copy it back into the system folders. So now let's learn block mesh. So now you can see that the mesh is generated. Now there is an important command in the for the dynamic mesh, so that is which is move mesh. So if you type move mesh, then this will move the mesh. That only it will not solve for the flow parameters, but it will just move the mesh. So you can also show that you can also see that there is an error thrown here. So it said that keyword motion solver is undefined in dictionary this the laminar horizontal and in this file. So in dynamic mesh dict, it says that the keyword motion solver is undefined. So the newer versions, uh, so in the newer versions, what it is required is in the older version, just the solver keyword was used. Now in the higher versions, so it requires keyword called. So you can see that keyword motion solver. So just you need to replace that with motion solver, motion solver. And okay, I think there was an error. Motion solver. Now let's run move mesh. So move mesh, it won't solve for the flow parameters like pressure, velocity. It will just solve for the deformation of the mesh. That is the mesh deformation. It will solve and so. So now you can see that our cases is now the case is running. So I was just trying to show that how in different versions the keyword errors can be present, and then the case then the case folder structure might be different. So you need to look at the errors in the terminal and then debug them accordingly. So I have already run this case, so I won't run this. I won't run it now again. So let me see. So this is the case that I have already run. So let me explain basically on the two important files, that is the dynamic mesh dict file and the point displacement file. So you can see that I have chosen the plunging amplitude as 0.5 meters and the frequency at 0.5 hertz, which means that my time period is 2 seconds. So for to keep that, according to this input parameters, so I have to make changes in the point displacement file. So before point displacement file, let me also explain the dynamic mesh dict file. Okay, there was in the constant, dynamic mesh dict. So you can see that the motion solver that we have used is displacement Laplacian. So there are various solvers in OpenFOAM that will accommodate the dynamic meshing strategies. So the one motion solver that we have used is that this is displacement Laplacian. There are other motion solvers like the velocity Laplacian, SBR stress, rotational. So there are many other types of motion solvers that we can use. So you can also look at the SRC folders and see the available motion solvers or the solvers libraries that are present in the OpenFOAM for dynamic meshing. So after we also choose choose the diffusivity value. So the diffusivity value chosen is the inverse distance. So the inverse distance means that the deformation will decrease as the distance from the moving body will increase. So as the cells from the moving boundary is will be far, the farther cells from the moving boundary will be less affected by the displacement of that boundary. So this means the inverse distance means that. So after we assign the solver, then we need to assign the dynamic parameters like the amplitude and the frequency. So we can see that the Australian displacement is used as the motion function, and we have used the omega as 3.14. If you calculate based on this parameter, so you will get these values. So if you get based on 0.5 Hz, and then we have used amplitude in the y direction at 0.5 meters. And another important boundary condition or the consideration to be made is in the U velocity boundary condition. So for the moving body or for the cylinder which is moving, so you need to assign the moving velocity in this case. So these are the important or the highlighted changes that needs to be made for dynamic mesh or for the moving boundaries. Okay, now let's see the results. So you have option to choose between reconstructed case and decomposed case. So in my case is still decomposed case. I have not reconstructed it yet. So decomposed case means that it is distributed in different processors. So I have not reconstructed into a single state. So if you run this case, then you can see how the deformation of the cells are taking place, meshes are taking place according to the movement of the boundary. So as we go farther, the inverse distance, as we have used inverse distance, that is, as we go farther away from the boundary in these regions, the cell deformation will be very less compared to the cells near the boundary. So you can, so after this, let's see here the velocity profile, velocity contours. So I have ran for the end time of 2 seconds because that is our time period. So I have ran for the one single cycle from mean position. So if you want to compute vorticity, then you can also do that. For that, you need to go to filters, alphabetical, and there is a filter called gradient of structure data set. So you can see that there is a gradient of unstructured data set is present as filter. So if you go there and choose velocity and then compute vorticity, and then you can choose vorticity from here. So we can see that the vortex setting is taking place in the cylinder, and the Karman and the vortex state is being formed behind the cylinder. So the vortex state will depend on the reduced frequency and the amplitude of the moving cylinder, Austrian cylinder. So that it might be the standard or the carbon vortex state, or it can be reverse carbon vortex state depending upon the reduced frequency and amplitude. So yeah, that's it for this case. So in this way, we can simulate the dynamic meshing or we can simulate the dynamic movement of the boundaries also using the dynamic meshing strategies available in OpenFOAM. So yeah, you can do other post-processing as well, like computing the drag and computing the drag coefficient, drift coefficient from ParaView also. So that is also done in previous workshops, so in the previous demonstrations. So you can check out those videos of the previous FOSSEE workshops also. So I think thank you all. Thank you all. I think you got to learn something from these short demonstrations. And if you have any queries, then please ask in the Q&A sessions.
Thanks a lot, Manjil. Yeah, so thanks to everybody, Ivan, Paris, Pranay, and Manjil. Okay, so now let me take you through the main site of FOSSEE. And first of all, let me take you to the cfd.fossee site, wherein you will get to know where are the resources and how to learn OpenFOAM using the spoken tutorials. So spoken tutorials are actually, they are audio video tutorials. They are just like a teacher or a tutor who is teaching in a class. So when a teacher teaches, he or she uses this a screen and also voice. So similarly, spoken tutorials are actually better teachers because you can pause them. Okay, you can rewind, replay, and learn at your own pace. Okay, so and it can be accessed from anywhere of the world and anytime. So no, this learning is independent of any particular time or even learning pace. Okay, so just I'm sharing my screen and I'll just walk you through our websites. Okay, so is my screen visible?
Yes, ma'am.
Okay, so first I'm opening the cfd.fossee.in website. Okay. Okay, so this is our website. So first I'll show you the resources that we have. So first of all, in the first point, you can see start learning OpenFOAM using the spoken tutorials on OpenFOAM. Just click on it. And you can see we have the instruction sheet, installation sheet. So please download and use them, okay, as and when it is needed. So you can just start from the installation. You can start from the very basics, setting up a case. So whatever knowledge you had gained today, okay, you will find it very relevant when you start learning OpenFOAM. Okay, so these are the basic level tutorials, and the last two are the intermediate level tutorials. So once you complete the whole group of tutorials that we have here, and also I'll send you by email all the references that you can use, all the links and some of the videos that I'll share after this workshop. So that will give you a complete knowledge to start off with the knowledge of OpenFOAM, and then you please try to attempt the screening task that we have given. So I'll let you know where the screening task is located and how can you access it and how can you register for the the autumn semester long internship of FOSSEE. Okay, so this is the resources. Now let me take you through the case studies. So we have a repository of case study projects, research migration projects, and all these projects are not developed by the team members of FOSSEE. We are only there to guide you, to mentor you, to teach you. Okay, but the final result will be produced by you only who are learning OpenFOAM using FOSSEE resources. So once you go click on the case study project, you can see this list. Just go to the completed case study project. You can see all these case studies, they are, contributed by students like you all. Okay, so we have this repository from our summer fellowship, our semester-long internship, and also the students of IIT Bombay who take courses, as a part of their course curriculum. Okay, so you can see many universities listed over here, and to access the complete case files, you can just click on any one of them. Whatever case study you find relevant to your study area, Okay, so you can download the abstract, you can download the whole case study. So here you can find the case files, the report, details, everything. Okay, so I'm not clicking here right now. Just go back after this workshop and do it yourself. Okay, so we have a similar repository for the research migration project. And because research migration project is a more time-consuming thing, I mean, it is double the effort that the students put for the case study project. So the list of completed case study project is you can see it is less than half of the case study project repository that we have, because these are all very power packed things that we have. These are the higher research level problem that we have in our repository. So if needed, you can refer to all these. Okay, this is the resources, and what else should I show you? So you can just explore all these tabs. So we have faculty partners from all over India and abroad. So all our faculty partners are listed over here. We have more faculty partners whose name are not listed over here. So eventually, as they complete their guidance, we will put their names. So he is Professor Chandan Bose, who is leading the team of OpenFOAM, and here are all the esteemed faculty members who are part of our team. So they are all guiding our interns, our fellows. Okay, and we also have a few members from the CFD industry who are our prestigious advisory board members. So they are all from the CFD industry, and they also guide the interns and fellows of FOSSEE. And once you work with all of them, you can get to know the actual problem that is being handled in the industry. So they actually float replica problems that the industry works on. So once you are once you gain the training in dealing with such problems, your learning will be far more advanced. Okay, so here is the contact us tab. You can just see. You can directly write to us here, contact-cfd@fossee.in. Okay, now let me take you to the main page of FOSSEE. It's very easy. It's FOSSEE.in, fossee.in. So here is our visionary ex-president, Dr. Abdul Kalam, who himself used open source software and for whom we have ISRO today. Okay, so here also this page is linked with our cfd.fossee.in. So if you want to know more about Python, if you want to know more about R, okay, so just click and you will be taken to the particular web page. So now let me show you how can you apply for the autumn internship. So this is the tab, internships, semester-long internship, autumn. Okay, and we have floated many screening tasks for various other software other than OpenFOAM. We have screening tasks for the eSIM team for electrical engineering, system administrator for core developmental part. OpenFOAM is here. So you can just click on it and you will see the screening tasks. You'll have to attempt any one of them. There are 2 screening tasks. Just click on it and this PDF will be open. So there are 2 screening tasks. You can do any one of them. Just select according to your background and preference and just submit it at the after solving this screening task problem. Just submit it at contact-cfd@fossee.in, the email ID that I showed you just now. Okay, so this is how you can apply, and you can register from here. See, the registration form is given over here. Just click and fill the form and attempt the screening task and submit it. It is that easy. And we will not look into any of your previous mark sheet or your academic performance. It is only you and your interest. Okay, so now we are open for questions. Any questions for us? So we have recorded the session, and within 2 working days, I hope we will be able to share the recording with you.
File, it's already in the YouTube. It's live now.
Yeah,
They can
it's
check on
live.
the
Yes.
Studio
So
IT
on
Bombay
the
channel.
YouTube, it is live, but if you can just copy paste the link in the chat box, Deepak, it will be helpful for them.
Okay. Yeah, sure.
Okay. So any questions? We are here for a couple of more minutes. Is it mandatory to install the both versions of OpenFOAM? Okay, Ivan or somebody can take this
Yes,
question.
ma'am. So, Abdullah, it is not necessary to install both the versions, but having both of them is a plus point because some cases that you're trying to run may work better on OpenFOAM 2412 rather than OpenFOAM 9 because the file structure is also different for each of those. So it again depends on what type of simulation you're trying to solve. If it is far complex and you require OpenFOAM 2412, then you can go ahead with it. But if it is something simple and if you're only trying to run a basic case and trying to basically learn OpenFOAM from the very beginning, I would suggest that go with OpenFOAM 9 because when our spoken tutorials are made for OpenFOAM 9, so you have all those materials readily available. Yeah. Okay.
Okay, one more tip is you just go to the spoken tutorial page that I showed you. You first try to learn using those. After that, like today is Friday, so by Monday, you all will receive the email with more links, more references that you can, use to learn OpenFOAM. But from today or maybe by tomorrow, you just go to the cfd.fossee.in webpage and refer to the spoken tutorials that I have shown you. That is the basic thing that you all should start learning from today. The screening test deadline is 15 September. Yeah, yes. So Evan wrote it. Wrote it. Yes. So regarding the submission deadlines and extend, we can also give extensions. So it is very important that you follow FOSSEE.in internships tab. Okay, and I am also very active in LinkedIn, so you all can get connected with me. I always keep on announcing about these internships and deadlines and, the link for the forms to fill up for the internships. So I always do that. But from your part, you please keep on checking the FOSSEE.in resources tab. So we will always update there at first. So if there are no more questions, we can conclude the session today. Okay, I think silence is the answer. Okay.
One doubt I have.
Yes.
Regarding that installation setup, sir had told that he had guided me previously before. Now I did that, but I'm not able to download the data sets. It's showing you have to download the required data sets, but this thing is opening. The ParaView Ubuntu 22 is opening.
Harshit, when exactly are you getting this error when you're opening ParaView or on a whole?
Sir, when I open the ParaView and they'll give a ParaView example visualizations. There, if I click this thing, it shows your installation does not have data sets to load the example.
Have you run the simulation?
No, sir.
Yeah, so if you're trying to view some results in ParaView, you'll have to first run that simulation and only then it will have some files that I showed you, right? When you run the simulation, you'll have after zeros, you'll have like 1, 2, 3, 4. So those files are necessary. Only then in Parafoam will be able to understand that you're trying to simulate and view something.
Yes, sir. Those files also, it's not there in my PC now. The files you showed in ParaView, and no files are here.
Okay, you can do one thing. Just Google for how, just first clear the whole thing. Just delete all of OpenFOAM, everything, and start from scratch. Because most probably something is not installed properly. That's why it is giving you an error.
Okay.
Yeah. So just clear the whole thing and start from scratch. Once you are doing it from scratch, you shouldn't get an error if you're referring to the PDFs that we've sent you.
Yes, sir.
Yeah, because I showed you also the exact same thing. I've not done anything different. So the installation should work fine.
Yes, sir.
Okay. Yeah.
Okay, sir. Thank you.
So the case, the internship, no, Ashish, okay, yeah, Professor Ashish Alice, yes. So yes, the structure of the internship is basically the faculty partners, they float problems. Okay, and we have a set of say 20 problems, and there are maybe 10 or 12 interns that we select. So we float the problems. We don't show them the faculty partner's name who is floating the problem. And, it is, it is actually a double blindfold method that we follow. So the students can see only the problem statements and they can select the problem statements likewise. And then according to the selection, we, connect the intern to the particular faculty partner. So in this way, the faculty partner who is floating the problem is unbiased because he or she doesn't know who is going to select the problem and and whom they are going to guide. And the students also, they don't know who is floating a particular problem. So so that their main focus is selecting the specific topics of their interest. In this way, they can work on the topics of their interest, and the internship is carried on. And it is basically online. Team members from the FOSSEE project, they act as mentors, and the faculty partners are the guides. So the guide, the faculty partners who are guides, they can, they may know OpenFOAM or they may not know OpenFOAM. So their job is just to guide the student on the conceptual part or the physics part of the problem. Okay, and the student is expected to know OpenFOAM and, solve the case using OpenFOAM. And if the student is facing any issue, our team members are there to handle it. So this is the basic structure of this internship. This internship will be for 3 months, just like the semester-long internship that we have in the beginning of every year. And typically it is 3 months, and the summer fellowship is for 2 months. The structure is like that. Extensions are given if depending on the performance of the student. So this is the summary of the internship. Can we apply as remote? Yes, it is completely remote. So nobody need to come to IIT Bombay. We only offer hybrid kind of fellowship for the summer fellowship only, not the semester-long internship. Internships are always online. This on-campus thing is only for the summer fellowship, that also in a hybrid mode. So some of the fellows, they come here in the campus and some do not come. So basically all the faculty partners are there from throughout India and abroad. As you see, like our team leader, Professor Chandan Bose himself is from UK. We have faculty members from Sweden, and students also are joining from countries like UK and in many other parts of the world. You can see Manjil, who just interacted with you. He's from Nepal. So we actually are connected to many people throughout the country and the world. So the whole framework is standing on remote or online thing. Okay, I hope we are done with the day. We can conclude the session. So thanks a lot for joining. I also thank all my team members. Excellent job today. And also I thank all of you to be, so much interactive with us. Thanks to the studio team also for supporting us. So Payal Mukherjee here signing off. Bye-bye. Stay connected. Bye.
Thank you, everyone.
Thank you, everyone. Have a nice day ahead.